Good afternoon, dear participants of the 5th Edge Computing Workshops. Today, times are not easy in our country, there is a war, but we scientists do not stop and try to continue working in our workshop. We are glad to welcome all of you in our workshop. So, we wish everyone an interesting discussion. And we invite to speak with the rector for scientific. Olena Denisuk. Olena, please.
Thank you. Good day, dear colleagues. Good day, dear participants and guests. For us today, it's an honor to welcome all of you in Cristobal Polytechnic State University, and it's an honor for us to hear all your discussions and see you researches. So I wish all of you today a productive work. Good discussions and good results at the end of the workshop. Thank you.
Thank you. And I want to say we have 28 articles we have submitted to our workshop, and the 13 of which were accepted for presentation of the result during today. A total of participants took part, including authors from China 7, from USA 3, Vietnam 1, and Ukraine 28. We are happy to see you all today, and now we invite the first author, and with her research is Yang Song, Human Way, and Dongwon Lee. Orest Kachan, you will speak.
Good afternoon. No, Zichen Li is present here, so he is going to present his paper himself.
Who must talk him?
One moment, please. Let me. Maybe you spoke too fast, and my colleagues didn't recognize. Mr. Yan Son. Mr. Yanan Song, you are invited to deliver your report. Could you please turn on your screen and deliver the presentation?
Yes.
Okay.
Dear participants, I'm Yanan Song from the School of Computer Science, Hubei University of Technology. Joining me in this research are Si Weiwei from CCCC Second Highway Consultants, CO Limited, and Donghua Liu from the Information Center of China Waterborne Transport Research Institute. It's an absolute honor to be part of this international online symposium and share our latest research on GADGN, a dual graph convolutional architecture for traffic flow prediction. We will start with an introduction that identifies the goals of traffic flow prediction as well as the main challenges and the solutions. Then we will move to the methodology section, focusing on our GADGN architecture design, experimental setup, and so on. Finally, we will summarize the research results and look at the future research directions. Traffic flow forecasting is crucial for urban traffic management and planning. So we aim to improve the accuracy of traffic flow prediction. However, we currently face two major obstacles. First, the traffic data collected by sensors is often implement. Most existing machine value processing models focus mainly on temporal dependencies and ignore the complex spatial temporal correlations in traffic data. Second, relying solely on predefined graph structures based on a priori knowledge or adaptive graph structures generated by node embedding cannot accurately capture the complexity and time-varying nature of traffic flow data. To address these issues, we have developed the GADGN architecture. It has two core modules, the GAN-TCT module and the DSGCE module. Among them, the GAN-TCT module is designed to fill in mission value by integrating LSTM, CNN, and transformer. It can capture spatial temporal dependencies more accurately, thus improving the fidelity and the spatial temporal consistency of the field data. The DSGCE module, on the other hand, fills both predefined and advantage graph features to extract more comprehensive spatial features. It generates advantage graph structures through node embedding and constructs predefined graph structures based on a priori knowledge and combines with an autoencoder to extract spatial features more comprehensively and capture complex spatial temporal information more effectively. As shown in the specific model framework diagram, the GAN-TCT module is used to fill the mission value more accurately. After the data filling in completed, it will be transferred to the virtual extraction module above for spatial temporal feature extraction. Specifically, the DSGCE module will extract comprehensive spatial features. These extracted spatial features will be fed into the gating mechanism, GRU, to dynamically adjust the update and reset gates of the gating mechanism. Through this process, the dynamic temporal features are effectively captured, and finally, the prediction results are output. To assess the performance of GADGN, we conducted experiments using two publicly available real-world traffic flow datasets from the PMS data, namely PMSD4 and PMSD8. These datasets are collected in real time from over 40,000 detectors in California, USA. Our experiments were carried out on a Win10 PC equipped with an NVIDIA GeForce RTX 2070 graphics card. We used 70% of each dataset as the training set, 20% as the validation set, and the remaining 20% as the test set. For performance evaluation, we use the three common metrics: mean absolute area, MAE, root mean square area, RMSE, and mean absolute percentage area, MAPE. We compare the GADGN with several existing models, including traditional models such as ARIMA and VAR. Static agency matrix-based models such as STGCN and adaptive agency matrix-based models such as Graph WaveNet and ASTGCN. As this table shows, GADGN outperforms these models in terms of MAE, RMSE, and MAPE on both the PMSD4 and PMSD8 datasets. This indicates that our GADGN architecture is more effective in traffic flow prediction and can capture complex patterns in traffic data more accurately. In order to show the performance difference between GADGN and other models more intuitively, we visualize the above tabular data as shown in figure. To further understand the contribution of each component in the GADGN architecture, we conducted ablation experiments. We removed the key components such as transformer, CNN, predefined graph, and autoencoder from the model one by one and retest it on the PMSD4 and the PMSD8 datasets. The results showed that removing any of these components led to an increase in MAE, RMSE, and MAPE values. For example, on the PMSD4 dataset, when the transformer was removed, the MAE increased from 18.29 to 18.63. The RMSE from 20.44 to 31.01, and the MAPE from 12.14% to 12.38%. These results demonstrate the importance of each component in the GADGN architecture for its performance. The GAN-TCT module in our model can actually capture spatial temporal dependencies, providing filling results that closely approximate real-world data. The DSGCE module effectively integrates static and dynamic agency matrix, enhancing the model's ability to learn complex spatial and temporal dependencies. In conclusion, our GADGN model improves the accuracy of traffic flow prediction to a certain extent. Looking ahead, our future research will concentrate on improving the computational efficiency and inference speed of GADGN model on edge devices. We also plan to incorporate external influencing factors such as weather conditions and spatial events to enhance the model's adaptability and extend its practical applications. The above is my research. Thank you for your attention.
Okay, thank you for your interesting presentation, and we invite everyone to take a part of the discussion. Who have questions?
Yeah, I have a question actually. Thank you for your presentation. Can you open the slide where you compare the different models with yours?
Yeah. Where you are
Can
different.
open the slide of the, well, yeah, exactly. Yeah, thank you.
Oh.
Yeah, I have a question. Can you, in broad strokes, describe what are the main differences between your model and the ones that are depicted?
Which one?
Like, for example, you say that most models lack the spatio-temporal analysis, and so maybe you can describe more precisely how your model captures this.
Thank you, but I need to conduct more research and thinking on this issue.
Okay, yeah, that's fine.
I have a question, if I may.
Okay.
Can I?
Yes, please.
Okay, thank you. So you propose an interesting solution, and in case if you are solving the problem of the route evaluation, interesting to know you are just selecting the proper route, or you are also selecting the faster delivery of the car en route. So that's mainly my question. Is knowing that there is a roadblock which is somewhere and your model evaluates, it's interesting which criteria is going first and which criteria is going next.
Next. On the one hand, we consider model compression techniques such as pruning and quantization to reduce the number of parameters and computational complexity of model without significantly affecting the model performance. On the other hand, the network structure is optimized to adopt lighter weight, convolutional, and recursive units to reduce the computational volume while ensuring the feature extraction capability. In addition, a parallel computing framework suitable for edge devices is explored to make full use of their hardware resources to improve computational efficiency and inference speed.
Understood. So in reality, as the manager of the traffic, which I have, for instance, in California. So let's think about Miami, right? So we have the coastal area where we usually have a high traffic and we have eight lanes directly in the road. So let's imagine that there is a big block right next to the coastal. So you definitely need to take away. So the question is, can I guarantee that escaping from the roadblock, I will still have a suitable route with the appropriate speed of getting to the delivery, to the location where I need to be?
Sorry, I need to conduct more research and thinking on this issue. I am afraid I can't give an accurate answer at the moment.
All right, thank you very much.
Thank you.
Thank you. Maybe someone want to ask someone questions? Okay. Thank you very much for your reports and your answers for the questions. And we invite the next speakers. The next speaker is Zhiqiang Li, and his presentation for article multi-UAV 3D path planning based on improved spiral search algorithm. Zicheng Li, are you here?
Yes, he is.
Maybe you or rest.
Okay, let me invite him. Maybe he is used to my language. Mr. Zicheng Li, you are invited to deliver your presentation.
Hello, everyone.
Hi.
Oh,
Hello, everyone. It's a great honor to be here today to present my work. My presentation is titled Multi-UOV 3D Path Planning based on improved spiral search algorithm. My name is Li Zhicheng, and I come from Hubei University of Technology. Today, I will introduce my research from 3 aspects: introduction, methodology, and conclusion. With the rapid development of UOV technology, it has been applied in many fields. To enhance the efficiency and the quality of UOV path planning, an improved spiral search algorithm is proposed.
The algorithm is easy to implement and has strong global search capability. However, it has drawbacks, such as a simple foraging strategy among sparrows. To address these issues, the improved algorithm incorporates chaotic mapping, competitive starvation mechanism, and adaptive differential evolution.
The sparrow population behavior in spiral search algorithm. The spiral population consists of 3 types of individuals. It's the discoverers, lead the search for food and guide the population, and the joiners. They follow discoverers to better foraging locations, and the early owners detect potential dangers and guide the population to safer areas. The figure is about the composition of sparrow populations. At the early stage of the algorithm, the initial distribution of individuals affects global search performance. To improve this, we introduce chaotic sequences for initialization. Chaotic sequences provide redundancy and uniform distribution, reducing the risk of individuals being concentrated in limited areas. This helps the algorithm explore the search space more effectively. The figure is about the 10 common chaotic maps. And the comparative hunger and to simulate food competition, we limited the amount of food each discover finds based on its fitness value. The higher fitness values mean more food found, and the joiners prioritize the most successful discoveries. The lower ranked joiners switch to less competent areas to avoid starvation. The figure is about the competitive machine. And if a sparrow cannot find food for a long time, it is replaced by a new sparrow, simulating nature population turnover. This helps maintain diversity and prevents primary nature convergence. The figure is about the hunger. And to further enhance search efficiency, we introduced an adaptive scaling factor F alpha, which adjusts the mutation operation based on the current population fitness. This balances exploration and exploitation, preventing stagnation in local optima. We compared the improved SSSA with other algorithms on 6 benchmark functions. The F1 to F3 mean high dimensional single peak functions. The F4 to F5 mean high dimensional multi-peak functions. And the F6 mean low dimensional multi-peak function. Results show that the ISSA achieves higher accuracy, faster convergence, and better robustness than traditional methods. The figure is about the benchmark functions. And the ISSA method was applied to a 3D mountainous tower model covering 118 kilometers. The experiment involved 4 UAV and 7 obstacle ranges. The figure is about the original map. This is about the fitness evolution function. The goal was to minimize path length, ensuring the shortest route, improve the path smoothness, avoiding unnecessary turners, enhance navigation efficiency and safety, enabling stable multi-UAV comparison. By optimizing the objective function, the ISSA ensures more efficient, safe, and comparative multi-UAV 3D path planning. In order to overcome the limitations of the spiral search algorithm, which is susceptible to origin on a local optimal and uneven distribution of interacts the population when searching for the optimum. Various improvement strategies such as chaotic sequencing, starvation deaths, and adaptive differential evolution were introduced to ascertain the efficiency of the algorithm. The algorithm is tested and compared with other algorithms on the benchmark function, and the experimental results show that the algorithm has better accuracy and robustness, which verifies its feasibility and effectiveness. The algorithm is applied to UAV path planning and simulated in a simulated environment, considering path length and safety. And the experimental results show that, compared with other algorithms, the algorithm outperforms the comparative algorithms in terms of accuracy, smoothly, coherency, speed, and stability. Thank you for your attention. Can you hear me?
Yes, we are hear you. Thank you for your interesting report. And we invite everyone to ask the questions. Who want to ask the questions? Valentin, please. We don't hear you. Please turn your microphone.
Sorry, I did not unmute myself, sorry. Quick question. So you were presenting the UAVs manipulation path detection. Interesting to know whether you are taking into account only the static obstacles or dynamics can be considered as well, and to what extent if they are just happening on the flow.
Sorry, I didn't hear clearly. Can I listen again?
Yeah, sure. See, if the UAV, which is unmanned aerial vehicle, is going on the path, so what it takes into account, only static obstacles like rocks or potential, I don't know, buildings, or there can be also dynamic obstacles taken into account, for instance, like big trucks or, I don't know, helicopters.
The path planning problem for UAVs mainly involves the selection and optimization of the path between the starting point and the end point in a multi-obstacle environment. The path planning not only needs to consider factors such as obstacle avoidance, short-listed paths, and minimum energy consumption, but also needs to cope with the complexity and dynamics changes of the environment.
So which means dynamics are also taken into account.
Sorry, I didn't hear
So
clearly.
dynamic obstacles are taken into account, right?
Yeah.
But interesting to know how. By what means? Well, how you consider it?
Here we set a fatalist evaluation function. We try to minimize the fatalist. The fatalist consider about such as the lessons, the lessons and the less path selections like this.
So for each segment, you try to detect if there is a dynamic obstacle on it, right? Okay, thank you.
Thank you very much.
Okay, Dmitro, please.
You told that you tested your algorithm in simulated environments. Could you please describe a bit what environments to use, what conditions did you simulate? Or at least short description of your environment where you were simulating conditions to test your algorithm.
I don't hear. Okay, thank you. Thank you.
Yes.
Okay, please, we invite you.
One moment. Dear colleagues, I'd like to introduce you the presentation entitled Studying the Efficiency and Performance of Vehicle Detection Method based on Feature Fusion and Attention Enhancement by Ming Xu, but I represent her because she failed to connect. The structure of this presentation is as follows: introduction, methodology, experiments, and analysis, and it is concluded by the conclusions. The main goal is to enhance the efficiency and performance of vehicle detection methods. And in this paper, it is proposed an attention and feature fusion based object detection algorithm to improve the existing YOLO V4 algorithm. And there are several tasks to achieve the goal. The first task is to employ a low complexity dense net as a backbone network for the detection model. The second task is to introduce the effective channel attention network to bridge the structure between the backbone and neck layers. And the third is the feature pyramid structure. It is used adaptive spatial feature fusion based on PenNet. It is added to the classical structure of YOLO to improve its efficiency and performance. Sorry. The general structure of YOLO is given here. It consists of input, backbone, net, and YOLO head. This structure is proposed to be improved. Input with some pre-processing. Input data is fed to the backbone. Backbone consists of several layers of dense block, with each with transition layer, and then FPN is given like this. It is a classic structure which consists of PenNet and SPNet are enhanced with ACA modules and convolutions and ASFF. And then it is followed by YOLO head. Let's consider closer to this structure. And first of all, we would like to consider dense net structure. It consists of bottlenecks, activation function, and convolution. Two convolutions are used to then concatenated with the input or bottleneck, and then dense block the conveyor of data processing is concluded with the transitional layer, which reduces the dimensionality of data. Then, effective channel attention. This block is based on SENet. It includes only a small number of parameters, but nevertheless, it provides significant performance gains. So this block ensures simplification of computations and provides good accuracy. The input data are subjected to global averaging pooling. Then this channel is processed here via the activation function and pairwise multiplied with the input data. adaptive spatial feature fusion can preserve semantic information and deliver it from low-level features to high-level features, and keep fine-grained details to leverage the semantic information throughout the model. Also, it is designed a loss function which consists of two components: classification error and classification error and the confidence error. Also, regression frame prediction error. These components of the loss function are given in this slide. To check the efficiency of the proposed methods, there were conducted several experiments. And first of all, there were compared the ablation experiments to study the efficiency of the proposed structure. And the first study was carried out for the basic YOLO v4 algorithm. Then it was carried out for DenseNet plus ECA, then DenseNet plus ASFF, and then full set of improvements. And we can see that the performance flops is considerably better for the proposed method than for the basic YOLO algorithm version 4. The same situation is with the parameters. Also, MAP was used to check the efficiency of the proposed network, model. The model. We checked the performance using 3 data sets: Erso, Byte, and Pascal. And we see that the proposed model works better than the baseline method. Also, we compared the performance of the proposed method with the existing methods. The set of the existing methods consists of YOLO v3, YOLO v4, combination of YOLO v4 and MobileNet v3, RetinaNet, and efficient DET d3. MAP for the proposed method is better for on both data sets. Also, flops is also better than for the most existing methods. Here we check components of models: DenseNet, backbone network model, ECA attention model, FIFI feature fusion model, and Mosaic data enhancement model. They are, we checked this efficiency of this combination of these methods and show that the full set of the methods works best. So each component is essential to achieve the goals and tasks declared in the very first slide. So we can conclude this presentation by the following statements. The replacement of backbone feature extraction network with a high-performing DenseNet leads to considerable reduction of model parameters. Then the existing FPN network model can be reconstructed and enhanced with the ECA attention structure to achieve the transition and transfer feature information between a backbone network and the next layer. and Ficci fusion structure improves across fusion, and optimization was also made for the loss function to improve the image processing. Thank you very much for your attention.
Okay, we thank you for your report, and we invite for the questions. Who have a questions to the speaker? Dmitro, please.
Thank you for your for the topic you presented. It was interesting, and you told you told a lot about the advantages of the proposed algorithm. Could you please describe the main trade-offs of the introduced algorithm in comparison with the others used in this area?
No, main trade-offs is that we use some specific algorithm of data pre-processing to have to gain full advantage of the proposed method, and also the modification of the structure is needed. So these are two main drawbacks.
What influence of these drawbacks?
Sorry, I didn't catch you.
So what is the probably main influence of these additional steps you made to the possibility to use this algorithm?
Data preprocessing helps us to improve the training process, because we more the information. Briefly, it can be described as follows: we combine four images on corners to avoid some overfitting. So this model is quite sensitive to the input data, and we need to pre-process it with the developed algorithm, which combines four images in the input data. So this takes some time, and also improvement of introduction of the additional modules to the classical structure also requires some work. So I think that say a layperson cannot use it at once. So we can some pre-processing is needed.
Okay, thank you, Valentin, please.
Yeah, thank you for your presentation. And the first question, mine is, I've seen the application, you are mostly focused on vehicle detection. In your presentation, I see that you are using the heat maps for let's say people for people recognition. What are other applications which you see for your model?
Mostly road detection of road traffic accidents, automatic processing of road traffic accidents, and recognition of traffic jams, mostly in this case.
So that it gives the best result. Okay,
yes,
thank you.
Yes.
Thank you. Anyone want to ask the questions? Okay, thank you. And we invite the next speaker. The next speaker is Denis Frihata, and his presentation, integration of edge devices and IoT to create a climate monitoring system for plants. Denis, please.
Hello, colleagues. Everyone hear me?
Me too. Yeah, all is good. You can continue.
Yeah.
One
second. Yeah. Today I'd like to present the results from our scientific lab PolyHub work that titled Integration of Edge Device and IoT to create a climate monitoring system for plants. Authors Nikita Prasol, Denis Furihata, Tetiana Vakaluk and Timofey Riganel. Кликер не працює, Ром. Наверное, через Zoom. 1 minute can't. Yeah. Recently, new tools and technologies have allowed us to create better system for plant monitoring. This system can send climate data to cloud servers for storage, analysis, and remote checking through apps. At the same time, the quick growth of Internet of Things technology is changing many areas of human life. IoT connects different devices into one network for exchanging data in real time. IoT is actively used in industries like medicine, agriculture, transport, environment, and energy. IoT allows devices to collect, process, and exchange data over the internet. It helps automate process, save money, and create new business opportunities. Major IoT companies like Microsoft, IBM, Cisco, Google, and Amazon actively develop IoT. Their innovations spread IoT solutions across many economic sectors, improving technology and everyday life. The research problem is about bringing new technology into household plant care. Our project aims to create a system that monitors climate conditions as plants grow and also designs the required device. Our article describes an IoT system for checking and controlling climate conditions of indoor plants. The system uses peripheral device to measure important indicators. This system helps assess how climate affects plant growth, which is important for their health. The Edge device for tracking climate conditions of indoor plants ensures the best conditions for growth, health, and good appearance. The device monitors key indicators and sends notification if conditions worsen. Our system is a part of an integration environment, creating comfortable and productive conditions in places like schools, offices, and homes. The system uses devices to monitor plant climate and send data using the MQTT protocol. The collected data is shown dynamically in an app, helping create optimal conditions for a plant growth. Modern electronic sensors greatly improve plant monitoring. These sensors accurately measure temperature, humidity, and light, reducing human effort. Built-in sensors monitor climate condition in real time, sending data to a central server or cloud for analysis. This allows quick response to environment change, helping maintain ideal conditions for plants. Using modern automated climate monitoring for indoor plants is very important for their health growth. Our system uses cloud computing and IoT, making it practical for everyday use. Our goal was to create a device that provides accurate measurements, long battery life, and easy use. It integrates with IoT using the MQTT for continuous data exchange with cloud service. The main part is a microcontroller that collects sensor data and sends it to the server if need. Another key component is a rechargeable battery need for device operation. A solar panel reduces charging needs and also works as a light sensor. All data is structured and stored on a server. Users can see all change on their device and perform detailed analysis for any period. Each component processes sensor data using specific algorithms, allowing climate monitoring and control via mobile device with internet access. We use various methods to design our plant monitoring device, covering technical, engineering, and design aspects. This helps to analyze device requirements and select the best materials and components based on functionality and efficiency. Its architecture. We develop a detailed software architecture diagram illustrating how system components interact. Edge device gather plant-related data, activating Kafka events, and distribute information instantly to subscriber services. Two main services manage data processing. The first is a socket service, provides real-time data updates via WebSockets technology, enhancing interactivity. And the second is a tracking service, stores data in the Influx database, enabling long-term analysis and trend monitoring. This structure ensures rapid response and comprehensive plant health management. We create a client application prototype based on this structure. This app receives data from sensors in an edge device, measuring soil humidity, temperature, and light. Its goal is to visualize data, analyze plant health, and offer timely care recommendations. After logging in, users access the main menu, the central hub of all system functions. Users can edit their accounts details here. Clicking Add Plant opens a page to set up a new plant. Users can enter the plant name and upload a photo or take one instantly with the camera. The page includes a drop-down list to select the plant type: indoor flowers, succulents, and herbs. The systems adjust care recommendation based on the chosen plant type. Users can link a device to the plant using Bluetooth or scanning QR code. For Bluetooth, the app shows a list of nearby devices. For QR code, the camera scans and automatically synchronizes data. The first plant page is a dashboard providing a quick overview of the plant status. It shows the plant name and photo. Next to the photo, current plant statistics display temperature, battery level, light, and soil humidity as clear icons with numbers and colors indication. Clicking the information block opens the plant profile with detailed edge device information. Users can edit plant details, view a larger photo, and see an interactive status scale with a green, optimal, yellow, warning, and red, critical zones. The scale combines collect data to show overall plant health. Graphs below, the scale shows detailed data on temperature, humidity, lighting, and battery power. These clear graphs tracks change through the day. Numbers of the left show parameters, ranges, and the timeline below covers 24 hours, helping user monitoring daily changes. Graphs are clear, separate, and visually consistent. And the last one, the figure shows graphs, visualization, daily plant health statistics. Below the graphs is a Unique port code for device identification and synchronization. A remove device button disconnects the device from a plant with a warning appearing before removal. In a summary, our system improves indoor plant care and shows how modern technology creates smart monitoring and control solutions. Testing and improvements continue. The device can monitor plants conditions in office, schools, hospitals, homes, and university. Thank you for your attention.
Thank you for your interesting report, and we invite 2 questions. Nadia, please.
Okay, great. Thank you. Thank you for your report, and I would like thank for organizers this seminars, because it's very important in our life, special today. We know that IoT system is very popular now, and it's technology industry 4.0. And I have a question, because this technology is very popular, and we can see a lot of system when used IoT technology. The first question is, what are the potential prospect for your system, and for your system experience in the integrations?
Okay, thank you for your questions. I will transfer it to the colleague.
Okay. Should I introduce myself? Yes. Okay, my name is Timothy. I'm one of the co-authors of this article. This system is designed modular, both on the hardware and software level, and this makes possible to introduce any new module, any new part of the system, both external and internal. We can introduce new devices in the system, introduce new port models, and we can integrate other apps, integrate some public APIs. We can replace some microservice with local implementation. For example, if we have a customer with a closed network on sensitive data, anything can be possible, then they can replace or add anything in their system easily because of the modular structure.
Okay, thank you. The next question. Okay, tell me please, what is the main difference between this development and numerous other similars?
Yeah, there is a couple of ones. First of all, that our device is a ready-to-use combination of the most necessary features. If we take a look at other products available to buy right now, they either don't have some features or have poor quality of their implementations, and our device tries to pack all of those in a ready-to-use device. Also, lots of high-quality devices and developments are focused on manufacturing plants. They're like mini farms, and they are used by actual farms for farming. And our device have a different purpose. It's meant to use as a normal pod. It tries to look and function as a normal pod, to be used, for example, in some facilities, in the university, in school, in a cafe, in your home, etc. Also, our device is not just a one device. As I've said, we have developed modular system, and our goal is to invest lots of our time, okay, in researches dedicated to modular systems and some optimizations, for example, distributing traffic among multiple devices to choose one of that is won't have the better battery, etc., to improve overall network performance, to improve battery efficiency, etc., and dive deep into those researches in modular systems.
Okay, thank you for your answer.
Okay, thank you. Maybe someone want to ask the question? Oh, yes.
Yeah, true. Thank you very much for presentation. Quick question. You just mentioned the farming application, which is quite prominent. What are the fallback scenarios for the case if the internet is disconnected, or if you have a potential loss of signal? What are the recovery mechanisms for the modular systems?
So, quick recap. Your question is about fallback reliability and how system reacts to, for example, network problems, right?
Exactly. If I'm using a farming case, so I have specific pod. So if I'm selling it and let's say it's a high quality product, I want to know the whole history. So what if I just have the disconnected humidity sensor or the temperature or whatsoever? I would love to know how the history is recovered if everything is back in place.
First of all, I want to specify that I've mentioned that other devices or alternatives are focused on the farming usually. Our device is not about farming, but a great question about reliability. A few things were considered during development of hardware part especially. The pod stores some amount of measurements for some period of time and stores its automation settings for all of these automations like watering, rotation to the sun direction, etc. And if the network fails, if the server is not accessible, if we haven't got a response from the server that the data is received, then we store this data until we got this response. And the next time the pod will wake up and try to send data, it will ensure that the last measurement it stores is also received by a server. And it works in both directions. Every time pod wakes up, the interval depends on the energy saving mode. It refreshes its settings. It asks server what are my current settings to automate, what are current conditions to maintain for a plant, and server sends actual data updated by a user, for example, from an app, and pod stores it into internal memory, voltage independent. It means that even if a battery fails, pod will keep its settings, and as soon as it will be turned on, it will keep on working.
Interesting enough. Thank you very much for the answer. But interesting enough, how you are thinking in terms of logging, just for beta maintenance of the system. So when you have the hiccups, or how you monitor it, which units are going offline faster or lower. So that perspective of the system.
Elaborate, please.
Yeah, indeed. So imagine that if I already have the full statistics recovered, right? So I still want to know when the temperature sensor was going offline, or when the signal was disconnected, or when the network was not accessible. Logging of such incidents is important.
First of all, some part of a backend, it's not shown on this diagram because it's a bit outdated. There are some endpoints designed specifically for devices. And if there are some errors occurred with both hardware or software or network, pod can try to report these errors. And they will be logged. For example, we can introduce some ticket system or alerting, etc. Also, there are some built-in features in MQTT protocol. There are some things like last will, online status, etc. So we can, for example, maintain the last time when the pod was connected to the network, and if the pod is not responding after some period of time, we consider it as an offline. And individual sensors are not we don't look at an individual sensors as an individual sensors. All the data is sent for a whole pod at once, even if it's collected in different moments, to improve network efficiency and because of its redundancy.
Okay.
Also, I want to add that we have a lot of local memory in our microcontroller. We have a slot of memory that can really long time work without internet, but without battery we can't work. So the main problem is recharge battery.
Understood. Well, I completely satisfied. I was just wanting, I was willing to understand deeper on what you presented, and definitely the fallback scenarios, especially for the monitoring system, is quite important. Thank you very much.
Okay, thank you. And Orest, please.
Thank you for your presentation. I'd like to ask about the sensors. Sensors are usually the least accurate and the least stable part of the measurement system. Do you use conventional sensors, or you and just connect them and do nothing to improve their accuracy, or you do some calibration or something like that to improve their accuracy? Because the accuracy of conventional humidity sensors is about error, sorry, not accuracy, error is about 20%. And also the light sensor is also of the same order of accuracy.
Okay, great question. For different sensors, different approaches were chosen. One of the most inaccurate sensors we've got is soil moisture sensors. We've used capacitive soil moisture sensors with different versions, version 1, version 2, etc. And they have really different ranges of values from different manufacturers and different versions. So we introduced we designed our firmware that way, so you can specify the range of values and some margins to calculate the actual value, because the output value, for example, for moisture is from 0 to 100%, and input value is a normal analog value. So there are some variables in all the formulas that maps one range to another, and those variables can be adjusted to improve sensor accuracy. Light sensors, their main inaccuracy is not in their essence, but in their position in the device. For example, if we have one light sensor on one side of pod, we can't measure other side. There are some leaves that can affect these measurements. So we introduced multiple light sensors on the different areas of the pod, and they're also extendable in case there are some leaves that covers them. And we calculate and compare those values to calculate the result one, depending on a formula chosen for a specific device and on its application. We haven't faced any significant errors on the humidity and temperature sensors we've used, but that's a great question. And also for each automation settings and each plant species, we have like normal behavior ranges, and we have conditions set it up. And if some values are, if we see some anomalies in measurements, we can react to them. For example, we can introduce anomaly detection AI to constantly keep an eye on all the measurements collected. And if it sees that there are some spikes or some not normal values in behaviors and measurements, it can report it.
Mm-hmm. So you focus mostly on the measurement data processing, but not on the metrological properties of the sensors itself. Is my assumption correct?
Partially, to some extent, and there is a reason for that. We are developing an end-user device. So one of the important aspects in making all of the decisions is the price of a device. And the more accurate sensor we want to use, the higher the price of the end device will be. And this makes a bit redundant some decisions. We can make a really accurate pod for a cactus that is staying on your table, and you will pay $100 for this pot. It's just an absurd. So we maintain balance between accuracy and price.
I see. I fully agree with you for your task, the accuracy is less important than the price. But in general, in such systems, there is a huge trade-off between accuracy and price, and the sensors and inadequate accuracy of sensors cannot be compensated on further stages. And in the measurement community, we say that trash in, trash out. So if your measurement data is highly inaccurate, you can't fix it later, because you have no traceability of your sensor to the standard, so you can't ensure accuracy of your data. It's like you use some custom line to without any information about the standard meter to measure the distance. So this, I understand you and your approach, but you should be aware of the situation that it's not always like this. Plants, it's okay, they can survive in very wide range of conditions, but in some more specific cases, especially in technical tasks, in industrial tasks, this approach may not work. So thank you for your presentation.
Thank you for your comment. Completely agree.
Okay, thank you. And we must have listening to the next after. And the next speaker is Dmitros Shevchenko, Bela Golub, and his presentation, regression analysis as a tool for identifying patterns in atmospheric air monitoring data. Dmitros Shevchenko, are you here?
Yeah, I'm here. Good day.
Okay, please start.
Give me a second. I'll prepare my sharing screen. Yeah. 1 second. Yeah. Hello, everyone. Do you see my presentation? Everything's okay?
Yes, we see you.
Okay, let's start. Thank you so much for this ability to present our scientific job. And you already told that it's a regression analysis as a tool for identifying patterns in atmospheric air monitoring data. We know that building monitoring system, it is a big challenge because the system should be reliable and stay accuracy and be available for everyone, and algorithms that process our air quality index should be full of ecology tendencies, I think, and we should focus for developing this system architecture and optimizations methods for improving and making and help us to make monitoring system more better and help with decision making. This scientific job, it is like a first step to trying to analyze dependencies between pollutants for analyzing air quality index in our ecology. So system architecture. On this slide, you can see our currently system architecture, and it's sliced to some layers. The first layer, it is your devices, stations that immediately collect, accumulate, and data from our air, from our environment, and that pollutant stores to our system by a few sources. It's like it can be directly by MQTT server, and it can be integrated by third-party services like a SafeEcoBot, maybe you know someone now, and KMDA. It is a government source where we can see air quality, and it is available for everyone. So after integrating the sources, all data validated and saved to our database. And the last one, it is a monitoring and I'm sorry. It is a monitoring and building some analytical processes like OLAP and connection data mining. But it's the next step, and today we will discuss about regression. On this slide, you can see a logical model of the database. I'll show you only the main tables that it is important for us. It is a station, measured unit, and breakpoints that used for index algorithms calculations, and measurements that collect timestamp and value and relation to station and pollutant. Our system already working, and for last 3 years we already collected almost 8 million records in our database, and we have realized own index calculation by world standards. Yeah. So we have a dashboard. On this dashboard, everyone can open the chart detail and see, select any pollutant, average type, period, and see situation about this pollutant index or temper, any pollutant that collected and stored to our system. It's like a fast, quickly mode to easy, quick analyzing situation, I think. Yeah. So the first question when we had after collecting this data, it's this algorithms working correct, and how or no, and how we can analyze dependencies between other pollutant, and how we can improve our algorithms for index calculation. And we focused on regression analysis and ordinary least squares. It's a linear type. It is a statistical method that minimizes sum of squared residuals. In simple words, it is a difference between actual and predicted values, with ability to find dependencies between independent values and many of dependent. But you can see that it's these algorithms draw exactly a straight line, and we can see the points. It is our data, and line, it is a real data, and if our points are close to the line, so this this pollutant can describe more efficiency our air quality index. And this algorithms, this regression type have advantages and disadvantages, and I want to show you that advantages that each number in the model shows how one factor affects the result, and it helps to see how the pollution levels are connected, and we can study and analyze many factors at the same time, and it is useful when we have a big list of measurement types that used for example, for our index calculation, I think. But it has some disadvantages. It is important in the end of the presentation we discuss about it, I think, that strange or incorrect data can give a wrong result. So we need to ensure our data set with correct, more correct data, and the next one, it is works best when things challenge. It is a straight line way, but nature doesn't always work like that. Yeah. So for that analyzing for this point, we develop some regression model in our system where we can select station, select period, regression type. Now it is only one, but in the future, I think it will be good to compare two type of regression with linear or non-linear and analyze which differences and which of them is better for monitoring system. So the next parameters like average type, it can be days or hours, and time periods, because we can select night, date, or when our traffic in the city is higher. So we can select what period we need to analyze. Then we select dependent measurement and in a list of independent measurements. And as a result, we see the percent of the variation that is explained by the independent variables. We can see the line and our data points and how our predicted data follows the line. Yeah. And you can see below this chart, we have a table where we can see that which measurement unit is more important or no for this data set. Yeah. And I want to show you, I prepared some short video with how our system works. So it's like an example that we have data and how you can quick analyze anything in our system. It's just example, but we have a big list of data just for more fast working, because our server is not it's not big, I think. Yeah. So we select a short period, select common air quality index, independent measurements, average type, it's hours, all 24 hours. And we can see that percent of variation, it's 31%. But when we select aggregation type days, you can see that our percent increased, and now it's like 79%. And when we select a few additional measurement units, our percents increased too. Not big increase, but we have some dependencies between this measurement. Yeah, and the next one is air quality index. Yeah, why I decided to show you that because I think it's important, because some ecologist or someone else can analyze. It is a quick instrument for analyzing situation in air quality and dependencies between pollutants. Yeah, and as a result, I want to see you that comparing between air quality index and common air quality index with different average types. You can see average type day and hours, and we can see that it is a different different sides, because these algorithms, these indexes has different algorithms for analyzing indexes. So common air quality index based on hours data aggregated data, and air quality index based on daily aggregated data. So we can see that linear regression is I think approve our thinking, and yeah, but I wanted to say that it is different for different periods, because in any different periods, your result and percent of your regression analysis can be different because it is in nature. So as a result, I want to say that this study shows that I think that we can use regression analysis for nature, but for improving our accuracy and reliability. And as a result, we saw that temper, humidity, and radiation, and some of other pollutant that now are not included to index quality index calculation. They have impact for prediction air quality. Yeah. So thank you for your attention. I want to say a few points additional for this. So it is a starting of analyzing, and I think that it will be good point to analyze not only linear regression, and analyze not linear regression too, and comparing comparing results for a big picture of this. Yeah. Thank you.
Okay, thank you for your interesting report, and we have some questions from Valentin, please.
Yeah, Dmitro, thank you very much for your presentation. And particularly what I was interested about is that you mentioned pollutants, which is very interesting. I've seen the graphs. Interesting to know whether you foresee the recommendations for managers and regulatory agencies regarding the actions which could potentially cause the air pollution increase. Do you plan to combine it with like infrastructure monitoring system, for instance, like recommendations of traffic decrease or validation of the nearby plant filtering system check?
Yeah, thank you for your question. I think it is a next step for us. I display on this slide that we have already built a lab kube, and we stored aggregated data for saving our aggregated data for. One second, I'll prepare the answer. So we prepare a lab a kube, and we will store all this data in 3 years to this move to this warehouse. And the next step, we will analyze that by some of data minings for optimizing our decision making, because it is one of the next steps that build a system with notification for decision making. And yeah, and it is a good point to include in the future traffic light. Yeah, because we can analyze points in which time our system had higher breakpoints, and category is dangerous for people, and we can. I think we can use it in future, because now we can only show that current state on the map, yeah, on the dashboard, but we traffic viewing, it's not well focused on our job. Yeah, thank you.
Yeah, this is definitely the slide which I was referring to, because you see the yellow marks, right? So this year, what we have seen, we already had passed the cross line, the red line, right? And where the air quality was really horrible. And for instance, if we are comparing Ukrainian cities with Europe, or with Asia, then potentially in such days, even the traffic of, for instance, even odd numbers on the street will be limited. So that's why I think combination with other system will definitely benefit to your system. Thank you.
Yeah, thank you for recommendation. Thank you.
Thank you. Orest, please.
Thank you for your presentation. You said that you consider only linear regression, but it's also possible to use the regressional analysis to fit some nonlinear regressions, such as exponential, power regression, polynomial regression. So you are not limited to just straight line. In addition, you can use multiple regression to study the dependence between the output variable and few input variables. So you can use a wider range of possible models, because in some cases it's obvious that the linear regression doesn't work well, but some nonlinear models will work much better, and your R squared will be much better and higher to follow the process. So are you going to use some more complicated models to your system, or you think it's enough to use just the linear one?
Yeah, thank you for your question. Obviously, it's not enough, and I told that in our system we have point to investigate some of another additional regression type, non-linear. Yeah, it will be nice to comparing this two results with similar data, similar period, so with similar data set to compare results for two different regression types. It is one point, and the next point we have already built a lab, and I wanted to analyze by data mining methods, search some association rules or data classification, and compare that results with our previous results with regression analysis. So I think it will be like a combination between several technologies, and it will be interesting to see the results. Yeah, thank you.
Okay, thank you. Volodymyr Artymchuk, please.
Hello, colleagues. Thank you, Dmitry, for your presentation. I have a little question. Is your system available for everyone? If so, send a link to it for the chat, please.
I can send. Regression analysis not available for everyone. You need to be signed in system. But if you wanted to see charts, yeah, I can send. 1 second. Please don't make the DOS attacks because server is small.
Sure. And as continues to a question that asked Valentins, who is the end user of your system?
Yeah, thank you so much. I think when we start to build to investigate this idea for developing this system, we had some of requests from the cities in Ukraine. It's like Nikopol city, and they had requests to our university to build that system for your government city. But we have that we have, and this contract was not finalized because the war started in Ukraine. And I think that this system that we are building, we can present to our government system, because not all of them, I think, that have this deeply analyzing system. Maybe I'm not sure. Maybe I'm mistaken. Yeah, but I think when we will finalize this analyzing, and we will have finalized analytical instruments, and that will help to with decision making, with improving index calculation. I think we can try to present that to our government system, maybe like a safe EcoBot, maybe they wanted to improve their system. I think it's like a nice question, and we need to we need to develop this idea, but when we will have finalized good results for a nice presentation and for visibility to sharing this realized instruments that can be used in other systems for improving our monitoring systems in Ukraine, I think.
Thank you. And one more little question. The quality of sensors are very different. And have you studied how the quality, especially low-cost sensors, are involved to the result data in your system?
I'm not understand fully, but you told that we are inviting some of sensors to connect to our system or something.
No. There are a lot of sensors, and most of them are low-cost sensor.
Low cost.
Low cost. Yeah, understand. And the quality of measurement from this sensor is not very good. And how we must to try to this information? Do you research this issue?
Okay, I understand. When we collect data directly from the MQTT server, we have some validation layer for if we analyzed the data is correctly or no. We have a list of breakpoints like for almost of measurement unit pollutant that are important for us that used in algorithms, and we validate that that this value exists in this breakpoints, and because sometimes I saw that stations where maybe some bug or something like that, because when we integrate and collect data from the CAMDA station, I saw that in the database we had tamper with minus 100 temper value for our city. It is incredible, and when we collect data, we're trying to analyze it. Yeah, maybe not of all, but almost that important. We have validation.
Yeah. Thank you.
Thank you for your question.
Thank you for your interesting report, and we must go to the next speaker. The next speaker is Alexander Chaban. Alexander Chaban, are you here?
Yes, I am.
Okay, please start.
Okay, let me share the screen. Please tell me if you see it. Okay. So, good morning to everyone. Thank you for having me here. Today I'll present our work, eMTKD at the Edge, an adaptive multi-teacher knowledge distillation for robust cardiac MRI classification. This research represents a collaboration between Khmelnytsky National University and Khmelnytsky Infectious Disease Hospital. We begin by exploring the background and significance of cardiac MRI, along with the challenges in automating its analysis, then define the specific problem and key contributions, followed by a detailed explanation of the proposed eMTKD framework, a review of datasets and evaluation metrics alongside experimental results and comparisons, and conclude with a discussion on the strengths, limitation, and future direction of the study. Cardiac MRI is a vital non-invasive tool. It allows detailed assessment of heart structure, functions, and pathology. Accurate and timely diagnosis using MRI is crucial for improving patient outcomes in cardiovascular diseases. However, automated analysis faces serious challenges. Domain shift is a key issue, where data heterogeneity from different scanners hinders model generalization. Data scarcity is another hurdle. Creating large annotated datasets is difficult due to the expert effort and cost involved. Privacy concerns and regulation also restrict data sharing, limiting dataset size and diversity. These challenges necessitate robust, generalizable, and privacy-preserving methods, especially for edge deployment scenarios. To overcome this data limitation, we explore techniques like knowledge integration and distillation. Knowledge integration merges information from varied sources. Knowledge distillation transfers expertise from complex teacher model to simpler students models. Multi-teacher knowledge distillation is particularly relevant. It allows a student model to learn from multiple teachers trained on diverse datasets, capturing a broader range of features. Our work specifically focuses on distilling knowledge from multiple domain-adapted teachers to create a robust student model for edge-based cardiac MRI classification. The central problem is achieving reliable cardiac MRI classification at the edge amidst several key challenges. Domain shift causes significant performance drops when models encounter data from new sources like different hospitals or scanners. Data scarcity limits the training of robust models as large, diverse, annotated datasets are hard to obtain. Strict privacy regulations further restrict the sharing of sensitive patient MRI data. Finally, edge devices themselves have limited computational power, memory, and energy, constraining model complexity. Our goal is to develop a framework that addresses all these challenges simultaneously, enabling reliable, real-time, privacy-preserving analysis at the edge. We propose EMTKD, which stands for Enhanced Multi-Teacher Knowledge Distillation. It integrates several key techniques. First, an adaptive teacher weighing mechanism dynamically balances teacher influence based on confidence calibration. This ensures the students learn from the most reliable sources for each sample. Second, domain adaptive feature alignment is used so teacher models learn domain invariant features. This enhances the student's ability to generalize across datasets. First, we integrate semi-supervised learning via pseudo-labeling. This leverages annotated data, reducing reliance on fully annotated datasets. Fourth, privacy-preserving techniques, specifically differential privacy, are implemented during student training to protect patient information. EMTKD aims to provide a robust, generalizable, data-efficient, and privacy-conscious solution tailored for edge-based cardiac MRI classification. This schematic shows the EMTKD framework architecture. It comprises three main stages. In the first stage, multiple teacher models are trained on different source domains using domain adaptation to learn invariant features. The second stage involves an adaptive knowledge distillation block. This block aggregates knowledge from the teachers using confidence weighing and attention. In the final stage, the distilled knowledge combined with SSL and differential privacy trains a lightweight student model suitable for edge deployment. Block 1 focuses on training multiple teacher models that can learn features which are invariant across domains. The aim is to train several teacher models, each on data from a different source domain. The process begins by initializing a teacher network and a corresponding domain discriminator for each domain. Each teacher is trained to minimize classification loss while simultaneously maximizing the domain discriminator loss. This is achieved using a gradient reversal layer, which supports adversarial training. This setup encourages the model to learn features that are helpful for classification but not tied to any specific domain. The outcome of this block is a set of trained domain-adapted teacher models along with their respective extracted feature vectors, ready to be used in the next stage. Block 2 involves combining the knowledge obtained from different teacher models in an adaptive manner. The goal is to integrate the knowledge in a way that takes into account each teacher confidence when applied to target domain samples. For this, each teacher prediction probabilities and confidence scores are calculated. Using these scores, adaptive weights are derived through a softmax function with temperature scaling, placing greater emphasis on the more confident teachers. Each teacher's feature vector is then scaled by its corresponding weight, and all are aggregated. This step may optionally use an attention mechanism for more refined combination. The result is a single aggregated feature representation for each target sample, which serves as a target for knowledge distillation in the next block. Block 3 describes the training of the student model, which incorporates distilled knowledge, semi-supervised learning, and privacy mechanism. The goal is to develop a compact and efficient model suitable for deployment on edge devices. Inputs of this block include the aggregated teacher features and target domain samples, which may be either labeled or unlabeled. The student model is trained to match the aggregated teacher features by minimizing distillation loss. For unlabeled data, SSL is used to generate pseudo-labels for samples with confident prediction, contributing an additional pseudo-labeling loss. A standard classification loss is calculated on the labeled data. The total loss used for training is a combination of distillation, pseudo-labeling, and classification losses. To ensure privacy, Gaussian noise is added to the gradients during optimization following differential privacy techniques. An optional fine-tuning step on labeled data can be performed to further improve the model. The final result is a trained privacy-preserving student model ready for deployment. Data sets and evaluation. For evaluation, we used two public cardiac MRI datasets with significant domain differences. Dataset A, the source domain, was the AC/DC dataset. It contains multi-center, multi-scanner data from 100 patients with various cardiac conditions. Dataset B, the target domain, was M&M's dataset. It features diverse scanners and field strength across 160 subjects, representing a distinct domain. Our task was cardiac MRI classification, focusing on evaluating generalization from source AC/DC to target M&Ms under domain shift. We use standard classification metrics for rigorous performance assessment, as you can see on the slide. Our setup used AC/DC dataset A as a source and M&M's dataset B as a target domain. Teacher models were trained on AC/DC with domain adaptation. The student model was trained on M&M using AMTKD, leveraging both labeled and unlabeled data. We used patient level splits. We compared EMTKD against several approaches, baselines like single teacher model, basic multi-teacher knowledge distillation, and DANN. We also compared against state-of-the-art methods, including Boost MIS and MTMS. Let's first examine performance on the source domain. The results show our proposed EMTKD achieves the highest scores across all metrics, including 95.3% accuracy and 97.5% AOC/ROC. This indicates strong fundamental learning and feature extraction capabilities within our framework, even before tackling domain shift. Now let's look at the target domain, dataset B, which represents a significant domain shift. Here, EMTKD demonstrates superior performance, achieving 88.5% accuracy and 92.5% AOC/ROC. This significantly outperforms the baseline STM and other methods, including the MTMS. This highlights EMTKD's excellent generalization ability across domains, validating the effectiveness of our combined approach. This confusion matrix provides details on EMTKD classification on the target domain. We see high true positive counts for both normal and pathological classes. False positives and false negatives are low, indicating high sensitivity and specificity. This confirms EMTKD effectively distinguishes classes even on this challenging target domain, resulting in 88.5% overall accuracy. Ablation studies helped assess each component's contribution on the target domain. Removing domain adaptation caused the largest accuracy drop, 7.3%, showing its critical role against domain shift. Removing adaptive weights decreased accuracy by 4.5%, underlying its importance for using teacher knowledge effectively. Removing semi-supervised learning led to 3% accuracy drop, confirming the benefit of using unlabeled data. These results show how the AW, and SSL all contribute positively and synergetically to MTKD's performance. Regarding computational cost, MTKD does require more training time, approximately 12 hours, and has a larger initial parameter count compared to simpler methods. This is mainly due to training multiple teachers. However, it's crucial to note that the final student model deployed on the edge can be designed to be lightweight and efficient. The main complexity resides in the offline training phase. These TS&E plots visualize the learned feature embeddings on target domain data. Plot A for MTMS shows moderate separation between source red and target blue features with some intermixing. Plot B for our EMTKD shows much clearer separation and tighter clustering for both domains. This superior separation indicates EMTKD learns more discriminative domain invariant features, aligning with its better quantitative performance and generalization. Our EMTKD framework demonstrates several key strengths. Its most significant strength is affecting domain generalization, vital for real-world clinical deployment. The adaptive knowledge fusion mechanism successfully integrates diverse teacher knowledge based on confidence. The SSL component improves data efficiency by effectively utilizing unlabeled data, reducing annotation needs. Integration of differential privacy provides quantifiable privacy guarantees for sensitive patient data. Ablation study confirms its synergetic effect, where the combination of techniques yields superior results. We also recognize certain limitations. The training phase involving multiple teachers is computationally intensive. Framework performance depends on the quality of initial teacher models. Several hyperparameters related to weighing losses and SSL require careful tuning. Future work will aim to reduce computational costs, perhaps via model compression or dynamic teacher selection. We also plan to explore stronger privacy techniques and further refine adaptive mechanism and hyperparameter optimization. In summary, we propose EMTKD, a framework for robust privacy-preserving cardiac MRI classification designed for edge devices. It integrates adaptive multi-teacher knowledge distillation, domain adaptation, SSL, and differential privacy. EMTKD effectively addresses key challenges like domain shift, data scarcity, privacy, and edge constraints. Experiments show significant performance gain, reaching 88.5% accuracy and 92.5% LOC/ROC on the target domain, outperforming benchmarks. Ablation study confirmed the positive contribution of each component. EMTKD offers a promising approach for deploying reliable AI diagnostic at the edge. Future work will focus on enhancing its efficiency and robustness. Thank you very much for your attention.
Thank you for an interesting report, and we invite to discuss. Who wants to ask the questions? Olaf, please.
You said you have multiple teachers for your students' models, but how do you determine which one produces the highest quality output for your features?
Basically, we are not choosing the best one. We are combining all of their outputs. So we can have features that are not what's better to say.
Excuse me for interruptions. My name is Paulo Duke. I'm co-author of this work and a colleague of Alexander's, I would like to clarify this question because I was more involved in this process. As Alexander mentioned, we do not specify and we do not calculate the highest rank of sum of teachers. We make an ensemble of those teachers and after that make a distillation out of this ensemble to prepare student work. And as you mentioned on one of the slides, there were some metrics which allowed us to measure the outcome of specifically a student model, not the teacher's model. So in short, we do not evaluate each, or better say, every student's model. Thank you.
And I have another question. What do you mean exactly by domains? Are domains mean like different means of collecting the data, or what exactly?
So basically different domains for us means different scanners, for example, as each hospital or even one hospital can have 2 or 3 different types of MRI machines. So that was key point.
So in the data that you use for training, if I correctly understand, there are like for the same patient measurements from different like mechanisms, or am I wrong?
No, it was for more than 100 patients.
Okay, thank you.
Okay, thank you. Orest, please.
Thank you. What type of MRI machine do you use? In particularly, what is the magnetic field in the used MRI machine?
It has, as I said, it has various of different type of MRI machines, as well as their range of field. So yeah, that's what we refer to under the different domains. So for each of the domain, we have a specific teacher model that focuses on the specific features for that particular domain. And also we have a teacher model that focuses on domain in relevant features as well.
If you may, I would like also to accompany my colleague's answer. To tell the truth, we cannot specify the exact model or some technical specifications of these MRI machines and as eventually MRI techniques, because all of them were stored in the publicly available data sets. One of the slides mentioned that it's AC/DC and MMS. Probably if we deep dive, we can extract this information, what technical characteristics of each machine were, but to tell the truth, we cannot provide them right now. I'm sorry for that.
Thank you. And one more clarification. Do you have any your specific images, or you use only the publicly available images?
For now, we used only the publicly available.
To the question, I would also like to add just a bit more notion. Our co-author, a medic from Khmelnytskyi Infectious Disease Hospital, advised us with some available information, provided consultations, but unfortunately we couldn't get necessary MRI scans because it's not that easy, because all of them are privacy. No, have privacy obstacles, which we unfortunately for now couldn't resist. Maybe when we reach some other institution, medical institution, we will receive our own MRIs. Thank you.
Thank you for your question. Thank you for your questions, for your answers. Thank you for your answers, and we invite the next speakers. The next speakers is Dmytro Shvaika, Andrei Shvaika, Dmytro Landyak, and Volodymyr Artemchuk. Dmytro Shvaika, are you here?
Yes, I'm here. 1 second.
Okay, please start.
1 second. Do you see my screen sharing? Yeah. Okay. So, so today I'm going to present our results of evaluating TBMQ. It's a MQTT broker, open source MQTT broker, and especially we evaluated it for P2P or point-to-point scenarios. So let me start telling you a little bit more about TBMQ. So TBMQ is a high-performance MQTT broker that we have been developing since 2020. From the beginning, the goal was clear. We needed a broker that could handle a high load, work under real tough conditions. So the idea was to create a broker that will be useful not just for small labs, but also for small scale deployments, but also will be useful for industrial IT and will be ready for any production lot. TBMQ was already used in a so we already have high load projects that use our broker, and at the moment of starting P2P testing, we already conducted 2 tests for fan-in and fan-out scenarios. It's like there are 3 scenarios of MQTT communication, 3 main scenarios. It's a fan-in, fan-out, and point-to-point. So fan-in, it's when like a lot of devices sending data to one application, or usually it's some IoT application. Fan-out, it's when we are sending from, for example, from that application back to that devices. And P2P, it's a little bit different scenario, and so we already have tests for fan-in and fan-out that prove that our broker can handle 100 million concurrent connections for fan-in scenario, and for fan-out use case, more than 3 million of messages per second with a single node of TBMQ, but for non-persistent clients. And so at the moment of starting, TBMQ was already fault-tolerant, scalable, and especially suited for low latency deployments and deployments that need reliability, where reliability is critical. So now I want to describe why P2P messaging matters in IoT. So in many IoT use cases, we don't actually want to broadcast all devices to all devices. What we need is private, reliable, and direct communication between devices. Imagine sending a command to open a specific gate, or sending a medical data from a wearable device directly to doctor's tablet or something like that. So illustration of that you can see on the slide. This is basically where point-to-point messaging comes in. It's about sending message directly from one device to another. And what is the challenge of this is scaling this, because we need to scaling to hundreds of thousands or even million of devices, and without losing reliability or speed of processing data. And this is what exactly we focused on. And before I will describe about our testing, I want to quickly show you the main challenges of P2P messaging in MQTT. So in P2P, every message must be routed precisely without shortcuts. And second, the broker's workload doesn't just increase, it explodes, because every new client, it's at a state of that client, it's at a session, and like routing complexity increase. And then you have reliability. In P2P, every message is critical because it's like communication from one device to another, and losing one message might mean missing a command or private data. And finally, edge deployments might make this even harder, because devices have often a limited CPU, memory, and unstable networks. And this challenge is making sure this all works smoothly in these difficult conditions. So on the next slide, you can see a diagram of our TBMQ cluster that we used for, basically we used it for our, so this diagram just show especially our final test, where we have 500 thousands of publishers and 500 thousands of subscribers. And so basically this diagram just outlines complete infrastructure of what we need in order to support this number of clients. All the communication, as you can see, was with the quality of service set to 1. And for subscribers, we use persistent clients, which means that like, so we basically use a clean session set to false, which means that even if device disconnect, all the messages will be stored in a storage, which is Redis, and like upon device reconnection, we will be sent that messages again to the client. And all of this cluster, everything was running on AWS EKS Kubernetes cluster, and this allows us independently scale Kafka, Redis, TBMQ nodes, as well as pods that we used for our publishers and subscribers. So let's check our test methodology. So test environment was AWS EKS cluster. We scale only horizontally under load. If you see that like we doesn't have enough capacity, we scale our instances. Test duration, so we are running 5 tests and only for 10 minutes. So the load was in the final test of like 1 million messages per second total. It's incoming and outgoing. So I mean, messages that go from publishers to broker and go from broker to subscribers. We have equal number of publishers and subscribers always, and quality of service was set to 1. So let's go to the next state. This is to the next slide. In this slide, I want to show you our test agent setup. To simulate the load, we built our test agent. It has basically 2 main parts: an orchestrator pod and runner pod. Runner pods acts as a publishers, and subscribers are runner pods acts as a publishers and subscribers, and they are balanced. So we have the same number of publisher pods and the same number of subscriber pods. The orchestrator, it's basically a pod that coordinates the runners, and also it monitors the system using additional tools for Kafka and Redis, called Redpanda and Redis Insight. So orchestrator pod, it can scale the runners smoothly as the load grows, and this allows us to make the test realistic and handle practical limits like network ports that we have during our tests. Next I wanted to show you our infrastructure overview. We selected instance types based on how each component actually uses system resources. So we have, for TBMQ nodes, we select more larger instances because they need more memory memory and CPU to handle high message through output. Kafka brokers use small instances, which were sufficient for our workload. And Redis also runs the same type of instances as Kafka. We don't need to have more like more larger size for Redis instances because Redis is a single threaded, and one node of Redis can use only one CPU core. So we decided that these instance types will be quite enough. Also we use Postgres. It's used for other entities that we store, like user like credentials and other type of entities in our system. Next I want to go to our performance results. So we are running basically 5 tests, starting from 200,000 and end with 1 million. And what did we get? We can see that the BMQ was scaled linearly. If we added more load, we just add more nodes. CPU usage stayed around 90%, which is on edge, but like for performance tests, this was enough. Message delivery latency stayed under 75 milliseconds, which was very critical for us because our goal was to not to get the results that will be that will be within 2-digit bounds. And acknowledgement latency was under 8 milliseconds, and also we got about 9,000 of messages per second per CPU core. which is really very efficient result. And even comparing to benchmarks of other public available brokers, this result is like quite bigger than like than the results of our concurrents, like but behind of all of this testing, the main issue was that at the beginning of the test, we noticed that the Redis was a bottleneck, and the problem was basically with oh, sorry, forgot to show you the slides about monitoring that we have during the test. It's a monitoring on one of our TBMQ node, which show the results of our CPU and memory usage. Also, this is our Redis Insight tab for final 1 million test that shows that we processed over 5 millions of comments per second, around 500,000 per one node. And yeah, so basically the main issue of our test was the Redis library, which is Redis client. And the reason for that was because it working synchronously and created a bottleneck when we push a lot of messages. Switching to another library, which is called Letus, which is asynchronous and native based. This allows us to unlock Redis full performance and get the results which we expect to see. So in a conclusion, I just can say that like TBMQ is scalable up to 1 million messages per second without degradation. It's reliable even when running at 90% CPU. It keeps latency low thanks to Kafka and Redis. And finally, it's ready for production, whether you're working with IoT, edge system, or large-scale messaging platforms. Thank you for attention. I will be happy to answer your questions.
Okay, thank you for your interesting report. And Dmitro has a question. Dmitro, please.
Thank you for your presentation.
One second. I'm for some reason hearing you very. Need to increase.
Better now?
1 second. Okay, continue, please. I don't know. I have some issues on my side, or it's only. Maybe it's my.
No, it's okay.
Oh. Okay.
1 second, please.
Yeah. Okay.
Do you hear me?
Yeah, I'm hear you.
Do you
hear?
Yes.
Okay. Thank you for your presentation. Quite relevant topic, and you said you showed that your system with your improvements have linear scalability. So do you predict it to be linear forever, or you foresee some changes in that in the future? And what do you think will be the complications you will need to overcome if you want to scale more than 1 million messages?
Yeah. So basically, during running these tests, we already saw small but degradation in latency. The plan was, as I said, to be inside 2-digit bounds, and like we are currently with 1 million, we are in this 2-digit bounds. But like, for example, when I run the first test for 200,000, if I'm not mistaken, the latency was around 40 milliseconds. So like from 200 to 1 million, we see a 30 milliseconds difference, approximately. And we definitely will be working on additional improvements, like to make it even faster, if it will be possible. We already have some ideas how to do that, by improving a little bit our design of Redis, interaction with the Redis. I'm not sure, but like we'll try to describe quickly. We are using currently such things as Lua scripts. It's so it's Redis supports Lua scripting.
Recording in progress. 1 second, please.
Yeah. Okay. Please let me know when I can continue.
Okay, let you continue, please.
Yeah, and like we are using these Lua scripts, and currently our Lua scripts are targeted to one client at a time. So the reason why we are using Lua scripts is because they provides for us atomic operations. So we can do a lot of operations on a different different data structures within a Redis, and do all of this safety, because our operations are atomic. But maybe the design was not the ideal, and we have as a future ideas improve the design, and we believe this will improve the performance even better.
Thank you.
Okay, thank you. Maybe someone want to ask the questions? Left, please.
Can you hear me?
Yes.
Yeah, do you have examples of systems where you use 500 around the big number of devices at the same time? So is it a big bottleneck for you if you need to increase this number of devices even more?
As I said, currently, like the main things that like we need is just add more like just horizontally scale. I'm pretty sure it will be work even with like more number of connections. And like, because I said that we have already a test for Fanin scenario where we have 100 millions of concurrent connections. We did this test not just we did this test because other public MQTT brokers do the test as well, like HiveMQ and EMQX. And we decided to check what our broker can handle that. And yes, we get that result. So it's currently designed in such way, so it's very easy to scale. And yeah, I don't know. But like you asked me if we already have clients or like if we have already deployments with a large number of connections,
Yeah.
I can say that yes, but like I can send you an image if you want with the statistics of I think I sent this to when I send a submission for this article to our conference. One of the recipient asked me to ask me if we use this in the real world, and we sent that screenshot from our production environment to him. I think I can find that and send this to a chat if needed.
Yeah, okay, it's fine. Just was curious.
Interesting. Okay, understood.
Okay, thank you. And now we
What can I just one more thing to mention?
Okay, please.
It's not mentioned in the presentation, but basically behind of that, we are migrated. Initially, we use a Postgres for. So we have two different type of persistent clients. We created our system so we can define two types of persistent clients. It's like application client and device client. So user, which is user platform, on its own decide which client he want to register as application and which client register as a device client. And application clients, they are fully work within a Kafka, but device clients, if you're talking about persistent clients, they are using Redis for persistent storage of messages. And in the initial implementation, before we run this test, Postgres was used for that persistent storage, and it was not ready for that load at all. So even with a single node test, local test, we get like a benchmark of I'm not remember 90,000 of messages per second, and that's all. And like since Postgres nature is that it's not scaling horizontally, we ultimately decided to switch to Redis. So that just one thing that I want to mention additionally.
Okay, we thank you for yes, it's very interesting. But now we must go to the next speaker.
Okay, yeah.
Viktor Malyarski and Vasily Oleksiuk. Are you here?
Yes, hello. Can you hear me?
Okay,
Hello?
yes, we hear you. Please start your presentation.
1 second, please. Okay. Can you see my screen?
Yeah, we can.
Cool. Good afternoon, everyone. I'm happy to present our work here on this workshop. It is an honor to take part to today's workshop to discuss the crucial aspects of modern edge computing systems. The topic of our presentation is a review of modern tools for edge computing system quality assurance. As technology continues to evolve, edge computing is becoming an essential component of our digital infrastructure. However, with its advantages come significant challenges, particularly in ensuring the reliability and efficiency of the systems. So during this presentation, we will explore 4 key aspects: why quality assurance is essential for edge computing system, the main challenges faced in this domain, how QA tools can be categorized and what their main selection criteria are, and the most effective and popular tools available for ensuring quality in edge computing. So let's move on to the first topic, why quality assurance is essential for edge computing system. Edge computing environments have become more popular and require a fundamentally different approach to testing compared to traditional cloud or on-premise applications. Software designers software designed for edge computing must be capable of effectively managing challenges such as intermittent connectivity, resource-constrained devices, and highly variable network conditions. These unique characteristics necessitate tailored testing strategies to ensure reliability, performance, and resilience in edge deployments. Quality assurance in edge computing ensures that systems remain reliable even when running across multiple edge nodes. Security vulnerabilities are minimized, preventing data breaches. Performance bottlenecks are identified and resolved early, and scalability is maintained as new devices and edge nodes are integrated. Without a robust QA strategy, business may face increased downtime, poor user experience, and security threats that could compromise critical data. Basic test strategies must be expanded and considered the requirements of an edge computing environment. So on this slide, we can see examples of workflow that should be considered during each step of basic test strategy. For example, during the test planning stage, we need to define scope of testing, define the main metrics we need to work with, and define the main edge scenarios that we would like to test. Then in environment setup, we will need to set up network emulators, configure edge nodes, configure monitoring systems. It depends on the test type that we will provide for the systems. On the test execution necessary to monitor all the results is the main purpose of the testing, and analyze step needs to identify the issues that we have during the testing. So what are the main challenges of testing? Despite its benefits, edge computing presents several challenges that make quality assurance more complex than in traditional centralized systems. The primary challenges include decentralized architecture. So unlike cloud computing, where applications run in controlled environments, edge computing distributes workloads across multiple geographically disparate nodes. Network variability. So edge computing relies on various network connection from high-speed fiber optics to low bandwidth mobile networks. Next one is security risks. Edge nodes often operate in less secure environments than data centers. Scalability and compatibility is also a challenge because edge computing involves diverse hardware and software environments, and also resource limits are always a bottleneck because many edge devices have limited computing power, storage, energy, as we already heard during today's presentations of the previous speakers. And QA tools must be efficient and lightweight to function effectively in this environment. So QA tools categorization and selection criteria. During this investigation, we discovered that there are different variants and ways of test types categorization, but there is no established separate categorization for testing tools. In general, we can suggest to categorize testing tools by their usage in different test types, like functional, performance, API, load, and so on. Also by test management area, that is test case management, bug tracking, logging, monitoring, and by general testing purposes like test data generation, device simulation, screen recording, and so on. Considering all the testing challenges and features of edge computing system testing described before, we can formulate a list of criteria to provide appropriate QA tool selection. So the appropriate quality assurance tools should be scalable, compatible, integrable, cost-saving, licensed, of course, and easy to use. Most of the criteria indicators can be assessed based on official documentation from software vendors or cloud service providers. However, such indicators as load handling, horizontal scaling, vertical scaling, stress testing, latency maintenance, and tool customizability should be determined based on expert assessment with subsequent verification of the respondent's degree of agreement. Suggested tool for edge computing system quality assurance. Based on research and industry best practices, we selected and systemized tools that can be suggested as the most suitable to perform needed workflows and assertions. Most of the tools of each type can be selected by certain project requirements, as they have similar purposes, but the similar purposes, but for example, different interface or a set of functionality differs these tools. We will stop on the one tools for each type just to show their main benefits for edge computing systems quality assurance. So let's start. First one is Clumsy. It's a network emulator. Allows users to introduce packet drops, latency, corruption, and duplication into a network to test the resilience of software or devices. While primarily designed for smaller scale or local testing environments, Clumsy can be highly useful for edge system developers to evaluate edge devices' behavior under adverse network condition during early stage development. Next one will be JMeter. It's for load testing, used to measure application performance, load, and scalability under various conditions. It's very popular in the context of edge computing. JMeter is particularly valuable for testing APIs, microservices, and edge-based app applications, helping organizations ensure these components can handle real-world traffic loads and response times. As for the security testing tools, we selected 3 different tools for different purposes. First one is Nmap. It scans edge devices for open ports, which is a key strategy to find network vulnerabilities or system misconfigurations. And second is Showdown. It's a search engine that can be used to scan, for example, IoT devices connected to the same network and find potential threats or vulnerabilities. And Metasploit, it's a framework for penetration testing to simulate attacks on edge devices and applications by supporting exploit matching, execution, and development. Next, moving to next types, it's monitoring and metrics. We choose Prometheus to highlight. It integrates well with edge systems to monitor the health and performance of edge devices and microservices. Prometheus is particularly suited for edge testing environment that require real-time insight into resource usage, network conditions, or system availability. End-to-end platform for deploying, so moving to the next type of tools. End-to-end platform for deploying and managing machine learning models in production is TensorFlow Extended, or TFX. It's often used in edge environment where AI models must run locally and on edge devices, such as image recognition in smart cameras or predictive analytics in industrial IoT. TFX enables model testing, validation, and monitoring, ensuring robust and accurate AI deployment at the edge. And as a test automation tool, we would suggest Catalan Studio. It's a versatile platform that supports web, mobile, API, and desktop applications. For edge computing, Catalan can automate functional testing of applications running on edge devices or microservices. Its simplicity and versatile make it ideal for testing interfaces, workflows, and APIs in edge environments. So in conclusion, as edge computing continues to shape the future of digital infrastructure, ensuring its quality, security, and efficiency remains a top priority. So by understanding the challenges of testing and selecting QA tools appropriately, we can help to build a reliable and resilient edge computing systems, saving costs, time, and so on for the development. Thank you for your time, and I look forward to answering your questions if there are so.
Okay, we have a question from Valentin. Valentin, please.
Yeah, thank you very much. It was really insightful presentation, very good systematized, let's say, availability of the tools. But I have more practical question to you. In one of my previous implementations, I had an interesting case. My testers were testing the Peacemaker. So what would you recommend me from your big deposit of testing tools, how you would suggest me to build the test suite for the Peacemaker, which is inside of the body?
Actually, I'm not that familiar with this type of system.
It's the thing which is stimulating your heart to beat.
Oh, okay, got it. So I think the first one, it would be great to use some tools that could provide stress testing for such devices, as I think it's the necessary part of testing of healthcare industry devices. So for stress testing, we will use some load and performance testing tools to make sure that these devices are working without any latency and any data breaks. Also, it would be great to have great monitoring and logging of the information that comes in and comes out from the such type of systems. And also, I think the main strategy is to be precise with the requirements to the devices, and always the QA strategy helps to save time developing these systems from scratch. So the more specific requirements are, the best strategy we can build to test the devices.
In development of my question, where do you propose me to put more efforts? In the time of project development, I mean, at the moment of the production of the Peacemaker, or at the moment of installation, or afterwards?
Actually, the best practice of QA is to get QA involved in all the processes of the development. So it should be involved from the stage of requirement gathering until the end of the release of the main product. So you need to be precise with requirements during all the stages.
What is the recommended time for testing? I mean, how much would you recommend me to test before installing it in the body?
Until you are sure that it's safe.
All right. Thank you very much. Thank you.
Thanks.
Thank you. Dmitro, please.
Thank you for your presentation. It's a very interesting overview. And like conducting your overview, you highlighted tools to cover different parts of the different areas, let's say, or different angles of testing IoT systems. What area do you think is still where do you think we require better tools or more tools? What area is least covered now? Which one you think needs to be developed to keep up to speed to the development of IoT systems and all the challenges we are facing in our cybersecurity and area, in type of cybersecurity, also in type of vulnerabilities of infrastructure, which is in high relevance for IoT systems. So what area do you think needs to be covered better or maybe everything's covered?
Thank you for your question. So I think as for me, there are four main types of testing that we should be focused on for such types of tools. It's a functional testing, mainly security testing is the crucial part. Performance load testing for ensuring the latency and that response time of this tools, and also I think the tools for monitoring are crucial as well. So I think the monitoring tools are the most valuable for all the types of edge computing systems, because it's the only way that we can track their quality.
And just describe it my question. So do you think all the areas are now properly covered, or you feel that, or some your analysis tells that some areas tools needs to be improved, or some additional approaches might be developed in some areas of testing for IoT systems?
Excuse me, not quite sure I understand your question right.
Maybe I will paraphrase. So you analyzed availability of tools to test IoT systems for now, and this area is developing quite fast together also with AI capabilities that can be deployed. Also, we see that global environment is changing quite fast. So, do you think that all areas of testing are properly covered by the tools available, or you think some areas need to be developed as in comparison to what we have right now?
Understood. Yes, of course, the modern technologies are developing very restrained for nowadays, and at the same time, the testing tools for them are developing as well. So I think every month we can observe new technologies that are coming to the market, and that's necessary to monitor all the new testing tools, or even the already existing testing tools and on the market. But to monitor their development, their new patches for their new releases, because usually they're adding a lot of, for example, AI-related functionalities that helps to work fast for now and be more precise with the testing. So of course, every day we can observe a development of this area, and we can just rely on ourselves, on our team, to monitor everything and to get the best strategies and best tools that we can.
Okay, thank you. Maybe someone wants to ask questions too? Okay, we are thank you for your interesting report and your answers. And we're going to go to the next speaker. The next speaker is Vadim Romanuk, Sergey Dementiev, and Svetlana Yarenko. Are you here?
Hello.
Hello.
Hello to all. Do you hear me?
Yes, we see you. We are hearing
Okay.
you. Let's start your presentation.
Great. Let me share the screen. Hello to all. I'm Sergey. I'm a lecturer of Vinica Institute of Trade and Economics. I'm like Embedded System World, and I want you to represent our job, an IoT-based system of mechanized export competition motion for perception improvement. Our goal is to develop a conceptual model of IoT-based embedded system, which allows visually tightly.
We don't see a presentation.
Sorry?
We don't see a presentation. Please start your presentation.
Oh, sorry. I look like not press the share. Okay, now is off.
Yes. Okay, yes.
Oh, great. Give me a second. Okay, so our goal is to develop the IT-based system which allow visually, tightly, and acoustically preserving location and motion of the sports players within the sports field. You know that any sports are popular for nowadays. Sports competitions like football, hockey, watched millions of people, and also for the last years, the competition for disabled people are also increasing. For example, you know that after main Olympic Games, usually initiated Olympic Games for their disabled people. So we offer a system for visual impaired people to better perceive information about events and games. Also, it will be suited for visual presentation, tactical and strategies for the sport games, for the team coaching and the sport staff. So here's the functional diagram of our project. You know, there are a lot of IoT-based sensor nowadays for tracking motion. You know about maybe cam for visual cam tracking system on the stadium, a lot of lidars, accelerometers, a variety of sensors on the players' clothing, on shoes, even inside the balls. I see a few projects that with embedded sensor accelerometers, hit gyro inside the ball, and it works pretty well. So all this information story in the stadium, record on the stadium, and story on the special servers. And it is possible to get some of this information for custom purpose. And generally, we can use a selected player's position to convert it into the mechanical marker that moves over the sport field model. These mechanized games field also have vibro motors that traditional to the tactical marker informs the observer about the critical game situation like foul, penalty, and so on. Also, headphone is possible to use with amplifier to hear the games more clearly. Okay, here's the moving diagram. We use the step motors to move the carriage. It's a diagram named H type. We also consider about the type like CNC machines, but it's more expensive and heavy. Also, we consider a T type and the similar type with a crossed belt. But we stay with this one because it's simple, cheaper, and easy to get any details to maintain the system because it's used for many 3D printers, and it's, let's say it's relatively cheap and easy to maintain. Basically, the motion in theater uses the two motors. When both motors rotate in the same direction, the carriage with the marker moves right or left. But when we need, when we move it opposite, the carriage moves right or down, and no problem to move the carriage diagonally using the one or another motor. We use a standard in MEA 17 motors. Here is characteristic. We use it because it is we selected this model because we need handle the torque that we needed, and it's also relatively cheap and it's standard. It's a standard part. And so the system core based on the Raspberry Pi compute model with the sensors, the initial and the final operation written on the Python. Science, it's easy to modify and support the high-level communication. But the movement core written by C++ language, because we need a maximum speed and fast control as much as possible. And we use 4-thread for that, especially for command, for thread for movement, for data thread, and give us ability to work in parallel to achieve the maximum productivity. Here's a part of code. We use it to calibrate and to set the marker on its initial position. It could be a center of the field or depending on the sport events we want to use. This table illustrates the timing characteristic. Sometimes characteristic is pretty old. Some of them it's possible to improve, of course, but we want to our goal to make the movement smooth near to the real-time movements as much as possible, and I think we achieve that. The next slide displays their power consumption. It's interesting things because we also plan to use this mechanical stand for the with a portable battery. So the main power consumption of our system is the motors, exactly. And but we have a few sleep modes, basically when the sport activity is not active for some time. Timeout happens and we release the motors by the driver settings. Also, once the game is over or there are no any movements for a long time, the system is moved to the deep sleep mode and we consume almost no power for that. Here are some pictures of development. Sorry. On the left side is a part of the field, and on the right side you can see the movement mechanism with the belt, pulley, and the carriage on the shaft. And we can try to have some video. It's a testing video. For testing purpose, we not use the data. We use a pad to try to move the carriage and fix the issues that we found to able to make movement as smooth as possible. And you can see the carriage move over the field. Okay, so in conclusion, we have suggested to conceptual model of IoT-based system for mechanical sport competition motion on a miniature sport field. It's operate on a Raspberry Pi compute model. This allows easier to visually, tangibly, and acoustically perceiving location and motion of player within the sports games. It could be data could be a stream and as well as some pre-recorded data. It has a compact portable size and reasonable power consumption. Thank you for your time. If you have any questions, please ask.
Okay, thank you for your effort. It's very interesting. Who wants to ask the questions?
Okay, I can question.
Nadia, please.
Okay. Thank you. It's a very interesting researching, and I have a question. What are the potential application of this technology beyond soccer, and how might the limitation of tracking only one player at a time be addressed in future interaction?
Thank you for your question. It's an expected question. We consider the area about how better to is it possible, of course, at all to move not only the one marker. Theoretically, for nowadays, it's really possible. It's possible to create a market, mechanized market with that self movement, move it across the fields, maybe control it using some BLE protocols or any others wireless protocols. But in really, it would be a product that not really possible to sell because it's for this concept is relatively cheap. But if we create expensive board with a lot of motor with complicated application, I don't think it will be useful. So we decided to stay a single marker to pay attention only the one point. And, but it's no problem to select for another player, and so we can check for absolutely different point, but not at the same time, of course.
Okay, thank you for answer. Maybe I ask you about future researching. What is expanded in this working you will be seeing?
Okay, thank you. Yes, we expected to check more providers for the data. For now, we use the sample data and the debugging using the pad and the data that we got from the internet. But ideally, my opinion, is somehow contact with the data providers that give us possibility to read the data, let's say, from the real game in the real time, not in real time, because almost all games have some shifting in their translation to able to reject some unwanted situation. So anyway, to receive a real data, parse it, and check how it will work in real life.
Okay, thank you.
Okay, thank you. Someone, Oleg, please.
Yes, the data you are talking about is the data like the movement of a player, or what data we are talking about?
It could be any data. Usually it's let's say it's a stream of data, like a CSV stream or JSON stream that consists of player coordinate, player acceleration.
I'm sorry. Can you repeat, please? Okay, let's go to the next speaker. Next speaker, it's one second, please. Sergey, yes, I hear. No. Okay, we are going to the next speaker. The next speaker is Oleg Kubylin and Alexandra Putyatina. Are you here?
Yes.
Okay, let's start your
Hello.
presentation.
Yes, let me share my presentation. Can you see the screen?
Okay, yes, we see your screen. Please start.
Good. So, my name is Alexandra Putyatina. I'm the senior lecturer at the Department of Informatics at Kharkov National University of Radio Electronics. And in this talk, I would like to introduce the alternative image model for video data that is represented as a series of images affected by the shot noise and compound Poisson process. This slide presents the structure of the talk. First, we will talk about a little bit mathematics, the jump progression equation for the noisy image. We will talk about two different types of noise, the shot noise process and compound Poisson process that corrupt the image. And then we will talk about the ways to deal with this noise and to restore the image, to filter it. In our case, it will be Kalman filtering. And at the end, we will talk a little bit about numerical result experiments and the result that we obtained. So first, I would like to talk about jump progression equation for the noisy image model. So we have, if we have a grayscale image, then we can represent it using the following jump progression equation. So the function f is the intensity of the image, of the true image. Xi and yj are the coordinates. Epsilon is a pointwise noise that corrupts this image. And I with index ij is our observed image. So this is our image with noise. So our aim here is to restore our image to find the real intensity function that is not corrupted by noise. So if we talk about a sequence of 2D images, two-dimensional images. A sequence, I mean, if we have a video and we have a sequence of images, then we can model them in the following way. We add here another index k, so for each separate image, we have index k here. All the rest is the same. We have the true intensity function, that is our real image, that is the function of the coordinates. This is corrupted by noise epsilon, and that's how we obtain our observed image. And once again, we need to restore the true image. This epsilon, the pointwise noise, can be very different. For example, the most common and the most easy to deal with is a Gaussian noise, the white noise. Many techniques are developed to deal with Gaussian noise, for example, Kalman filtering is the one that we are using here. But what if we have not an easy, so to say, noise here, not white noise, but, for example, shot noise, the noise with jumps. So what can we do in this case? How does the shot noise, how does it look like the shot noise, and how it is defined? So the shot noise is defined in the following way. Lambda, it's a lambda t, we define it, we call it lambda t here. And you can see this is lambda 0, the initial value, but what is important here, you see we have the sum of yi, where y is a sequence of identically distributed random variables that can have different distribution functions. It can be a normal distribution, it can be student distribution, it can be log normal distributed, it may differ. What is m here in the sum is a sequence, first Si here. Si is a sequence representing the event times of the Poisson process M. So the Poisson process M, it drives the whole process. It gives us these time points at which the jump of the height yi occur. And we can see here an exponential term in the minus delta power. That means that after the jump happens, it slowly reduces. I will show the graphical representation on one of the next slides. So this is a complicated type of noise. It's not really well studied at the moment. So, and no explicit solution for filtering problem, for the problem of restoration the image can be obtained. So the best way is try to approximate the short noise process. How can we do it? So this is the structure of the short noise. You can see that after the jump happens, it slowly diminishes. After the next jump happens, the height of the jumps is defined by this random variable yi, and the rate of decay is defined, so how quickly it decays is defined by delta, by the parameter delta. So in our paper, we have used the result that short noise process can be approximated by its Gaussian approximation in the following way. So lambda t with a hat is a short noise approximation. Here zt is a Gaussian random variable. This term is just the mean value, the expectation of the short noise, and this term is just the standard deviation. This approximation holds if the jump rate is quite high and the jump height is not very big. In this case, the approximation, the short noise can be approximated by Gaussian, random variable by Gaussian noise with such a correction term. And what we have there, we just look at our image sequence and substitute short noise in the place where we had epsilon, any noise. We have now short noise. And we approximate short noise. We use not lambda, but lambda with a head, and substitute here this Gaussian approximation. And this is just a constant correction term. It's a correction term that goes here to the intensity, to the true intensity of the image. And this is the Gaussian random variable. So after approximation, our model of the noisy image is simplified in the following way. Now we have no short noise here. We have a Gaussian noise, and it becomes much easier to deal with such kind of noise and perform the filtering process. Another type of noise that we can use is a compound Poisson process. It's defined in the following way. What's the difference with the short noise? You can see we do not have this decay coefficient. We don't have this decay term that we have had in the short noise. E to the power of minus delta. We have just the jumps, the sum of the jumps. Under certain conditions, when the jumps are not very big and they happen quite often, compound Poisson process can also be approximated by a normal Gaussian random variable with a correction term, and all the previous steps can be repeated. So what do we have now? Returning back to this model or to this model. We don't have anymore the short noise process. We have just the Gaussian process, and we can use any of well-known and well-performing techniques for filtering our true intensity, image intensity. For example, we use here Kalman filtering. In this conference paper, in this talk, we use Kalman filtering. I'm sorry, my presentation. I'm really sorry, this is the problem with my laptop. The presentation just disappeared.
Please restart your PDF file.
Yes, sure. Just a moment, please. Can you see the screen now? Oh.
We can't.
No, it's a black screen.
And now it's in?
No, we don't see your screen.
And now you can see it?
No, we don't see your screen. Please recollect. Maybe we go to the next speaker and you come back after them.
Okay.
Okay.
Okay. I
Let
don't.
me check here. Олена Наумчак, Ігор Прикевич, Микола Романчук, Дмитро Федорчук, Леонід Наумчак. Are you here? Olena Naumchak, we don't hear you. Olena Naumchak, we don't hear you. Okay, Olena, are you here? Okay, maybe Andriy Golhatin, are you here?
Yes, I'm here.
Okay, Andriy, let's start your presentation while our speaker
Okay.
connect to our meet. Okay, we see you, we are hear you. Let's start your presentation.
Can you see presentation?
Yes, we can receive our presentation here. Let's start.
Thank you. Good afternoon. Today we will be discussing the frontier of deploying large language models at the edge. As we know, LLMs have dramatically transformed natural language processing, but they present a significant challenge when deployed on resource-constrained devices. Models like GPT-3 with 175 billion parameters require about 350 gigabytes of memory for inference, while most edge devices have only a few gigabytes available. Our research explores the techniques and frameworks that make efficient edge deployment possible, balancing performance with the trends of the edge computing. Several open source frameworks have emerged to facilitate LLM deployment on edge devices. For example, TinyAgent provides pre-trained models optimized for edge deployment with accurate function and efficient inference capabilities. MNN LM addresses memory and latency challenge through techniques like quantization and hybrid storage solution. H2 GPT offers a range of fine-tuned models and no-code interface that simplifies the deployment process. These frameworks are making edge-based LLMs more accessible and practical across various applications. When comparing these frameworks, we see that TinyAgent demonstrates the highest inference speed and memory efficiency, making it particularly well suited for real-time application on resource-constrained device. MNN show strong performance with its mobile-specific optimization, while H2 GPT provides versatility with its range of models. The choice of framework ultimately depends on the specific requirements of the application, the capabilities of the target device, and the performance metrics prioritized by the developer. Several key techniques enable efficient LM deployment on edge device. What is it, these techniques? It's quantization, reduced the precision of model weights and activation. For example, some of model like HOTA-Q is a good example that gives 4/8-bit quantization with comparable accuracy to full precision models. The next techniques is pruning. Pruning removes redundant parameters, creating sparse models that require less computation and memory. HLM generates pruning sparsity and quantization bit width policies for efficient deployment. Knowledge distillation transferred knowledge from a large teacher model to a smaller student model. Distilbert achieves 95% of BAT's performance while being 40% smaller and 60% faster. Adapter tuning fine-tunes small adapter models while keeping the base model fixed, reducing memory and computation requirements for adaptation to specific tasks. These techniques offer different trade-offs between model size, inference speed, and accuracy. Edge cloud collaborative frameworks represent a hybrid approach that leverages the advantages of both environments. These frameworks offer several key benefits: scalability through distributed workloads, efficiency by offloading computationally intensive tasks to the cloud, adaptability to varying network conditions and device capabilities, and enhanced privacy by processing sensitive data locally. Notable examples include EdgeShard, which partition model as adaptively selects devices, EdgeLM, which use adaptive quantization and caching mechanism, and PAC, which enables efficient personal LLMs, fine-tuning through parallel adapter and activation caching. This collaborative framework help bridge the gap between the computation requirements of LLMs and the resource constraints of edge device. When comparing this collaborative framework, we observe different strengths across key performance metrics. EdgeShard demonstrates the lowest latency, making it suitable for time-sensitive application. HLMs excels in memory efficiency, maximizing performance on device with limited memory. PAC achieves the highest throughput, enabling efficient processing of multiple requests. The choice of framework should align with the priorities of the specific application. For interactive service requiring quick response, EdgeShard might be preferable. Application with severe memory constraints might benefit from HLMM. High volume processing tasks could leverage PAC superior throughput. It's worth noting that all three frameworks significantly outperform traditional cloud-based deployment approaches in this matrix. Several optimization techniques enhance LLM's inference in Edge Cloud collaborative framework. Adaptive quantization dynamically adjusts the precision of model weights and activation based on device capabilities and application requirements, achieving significant latency reduction. Reinforcement learning based scheduling learning optimal task allocation policies through interaction with the environment, considering factors like communication overhead and computation time. Vector databases and caching mechanism store frequently accessed model parameters and intermediate results, enabling efficiency reuse of computation across inference requests. Our research shows that adaptive quantization achieves the most significant latency reduction, while vector databases and the caching mechanism demonstrate the highest throughput improvement. In practice, combining these techniques offers the best performance and efficiency for LLM inference in Edge Cloud Collaborative Framework. Hardware acceleration solutions are crucial for efficient LLM deployments on edge device. Cambricon LLM integrates a neural processing unit with NAND flash, enabling inference of models with up to 70 billion parameters on edge devices. It achieves significant speed up compared to existing flash offloading technologies. AXLAM leverages POSIT-based multipliers and high bandwidth memory to deliver energy-efficient acceleration, achieving a 9-fold reduction in energy use and 58% decrease in area compared to state-of-the-art alternatives. DTA Trans and DTQ Aten represent hardware-software co-designed solution that use dynamic mixed precision quantization and variable speed systolic arrays, delivering substantial speed up and energy saving. Our comparison shows that Cambricon's LM excels in speed, while AXLAM and DTA Trans DTQ Aten offer superior energy efficiency. Several emerging trends in hardware acceleration are shaping the future of the edge-based LLMs. Heterogeneous integration combine different specialized accelerators like NPU, GPU, and FPGAs into a single chip or package, enabling efficient handling of diverse workflow types. In-memory computing used innovative memory technologies to perform computation directly within memory, significantly reduce the data movement overhead between processing units and memory. Sparsity-aware architecture capitalize on the inherently sparse nature of LLMs, reducing computation and memory demands during inference. And we can see any trends like adaptive precision techniques and hardware-software co-design for optimized hardware architecture, software stack, and algorithm to create a cohesive solution tailored to specific device and application. These trends collectively point toward more powerful, efficient, and specialized edge device capable of supporting increasingly sophisticated LLMs-based applications. Edge-based LMs enable sophisticated IoT and smart city application by processing and analyzing real-time data streams directly on the edge devices. In traffic forecasting, LMs leverage spatiotemporal modeling to predict traffic conditions accurately, optimizing transportation infrastructure and reducing congestion. The LSG-LM model demonstrates superior performance in large-scale traffic flow forecasting through edge cloud collaboration. For anomaly detection, edge-based LMs model normal behavior of IoT design and industrial equipment, detecting deviation in real time and triggering appropriate actions. Blockchain-based framework enhance this capability by enabling secure collaborative training and inference across multiple edge device. This application follow a workflow where IoT sensor collect raw data, edge device processed it using LLMs, cloud server provide additional analysis when needed, and inside feedback to application that control the IoT environment. This approach enables intelligent, adaptive, and responsive IoT and smart city system with reduced latency and enhancing privacy. Edge-based LLMs enable personalized services and human-machine interactions that understand or respond to user needs in real time. Intelligent personal assistant integrate multimodal interaction capabilities, processing speech, vision, and text inputs to provide context-aware responses. Our research highlights an edge-based autonomous AI system that uses a combination of on-device and cloud-based LLMs to deliver high-quality, low-latency, and privacy-preserving assistant. Personalized recommendation system leverage LLMs to create user profiles, analyze feedback, and generate tailored content. A federated learning framework enables collaborative training of recommendation models across multiple edge devices while preserving user privacy through techniques like differential privacy and secure multi-party computation. The workflow involved user providing input through various modalities, edge-based LLMs processing this input to generate personalized responses, and user feedback refining the models over time. This approach delivers more natural, intuitive, and tailored interaction compared to traditional cloud-based solution, while reducing latency and enhancing privacy. Multimodal edge intelligence integrates LLMs with other AI domains to process heterogeneous data streams in real time. In robotics and autonomous systems, edge-based LLMs enable more natural and intuitive human-robot interaction, as well as more robust adaptive behavior. Pre-trained vision language models are applied to recognition tasks in robotic application, allowing robots to understand and respond to visual and linguistic cues. For computer vision and video analytics, LM enhance scene understanding and object recognition through cross-model learning capabilities. The architecture illustrates how multimodal sensor collect data. Different AI models process their representative input. Edge-based LMs integrate this processing into a coherent semantic representation, and the resulting multimodal outputs guided future actions. This integration creates a closed-loop system that can adapt to dynamic and unstructured environments, significantly enhancing the capabilities of edge device. Several cases demonstrate the practical impact of edge-based LMs across different domains. For example, if we look at the autonomous edge AI system, we can see example like using edge LMs to deploy in smart homes, connected vehicle, and personal robotics. LM-powered smartphones optimized deployment framework for mobile device. This is on-device virtual assistant, real-time translation, personalized recommendation, etc. And personalized digital avatars integrate LMs with speech synthesis, recognition, and computer vision to create natural and expressive interaction. They find application in customer service, tutoring, and social companionship, demonstrating potential to enhance engagement and create immersive experience. This real-world deployment highlights the feasibility and benefits of edge-based LMs across diverse applications. Despite significant progress, several challenges and opportunities remain in deployment LMs on device. Resource constraints continue to be major challenges. Addressing this requires advanced compression method, novel architecture like mixture of experts and efficient hardware acceleration co-design these software components. Privacy and security concern are paramount, especially when processing sensitive user data. Domain-specific adaptation is crucial for optimal performance. This involves fine-tuning with domain knowledge, developing modular and composable LMs with plug-and-play component, and exploring interactive learning paradigm that incorporate user feedback. And scalability and interoperability in heterogeneous environments require flexible middleware, standardized interface like ONNX, and decentralized architecture that enable seamless communication and coordination across devices. These challenges also represent opportunities for innovation and advancement in the field. Several promising research direction can advance edge-based LLMs and unlock new opportunities. It's integrating edge-based LLMs with other AI technology, like reinforcement learning, graph neural network, and knowledge graph, can enable more intelligent and context-aware decision making and reasoning in edge computer environment. exploring multimodal and cross-lingual application such as image captioning, video summarizing, and machine translation can enable more natural and expressive interaction between human and edge device. Developing edge-based LLMs for mission-critical and safety-critical application require ensuring reliability, security, and performance in real-world environment. This includes application in autonomous driving, industrial control system, and healthcare monitoring. Investigating sustainable and green computing approach consider energy efficiency, carbon footprint, and environmental impact of edge-based LLMs. Techniques like energy harvesting, workload consolidation, and renewable energy integration can reduce ecological footprint. Studying social, economic, and ethical implication ensure fair, accountable, transparent, and explainable deployment of edge-based LLMs guided by responsible AI principles. This direction collectively highlights the transformative potential of the edge-based LLMs in shaping the future of intelligent computer systems. In conclusion, our survey has explored the rapidly evolving field of the edge-based large language models, which bridge advanced AI capabilities with resource-constrained edge device. We've examined key enabling technologies, including compression techniques like quantization and distillation, collaborative frameworks such as EdgeShard and EdgeLM, and hardware acceleration accelerators like Cambricon LLMs and AXLAM. This advancement have unlocked diverse applications across IoT and smart cities, personalized services, and multimodal edge intelligence, as demonstrated as real-world deployment. The significance of edge-based LLMs extends beyond technical achievements. They represent a paradigm shift in AI delivery by enabling low latency, privacy preserving, and context-aware AI at the edge. This model democratizes access to cutting-edge capabilities. Looking forward, continued innovation will address persistent challenges like resource efficiency, privacy, and scalability, unlocking transformative possibilities from autonomous system reasoning in real time to personalized service adapting instantly to user need. Our vision is that the edge-based LLMs will reshape computing, bringing intelligence closer to user than ever before, and fostering a world where AI is not just powerful, but personal, pervasive, and profoundly impactful. Thank you for your attention. I would be happy to answer any question you might have about our research on edge-based LLMs.
Okay, thank you for your interesting report. Who want to answer the questions? Oleg, please.
Yeah, thank you for your very insightful mapping study. Probably the only question I have is, have you reviewed or will you be in the future like the usage of agentic AI? Have you researched it? Probably it's very appropriate for edge-based LLMs to have more collaboration, as you said, between each other.
Thank you for your question. For now, it's this server aims to provide an overview, this emerging field about edge-based LLM. For next research, we think about not create not only overview of this model, but also try the some suite of this instrument in real case, no, like some practical models, etc.
Okay, thank you.
Okay, thank you. Who wants also ask the questions? Okay, thank you for your presentation and your answers for the questions. And we go to the Alexandra Putyatina. Alexandra, are you here?
Thank you.
Yes, I'm here. I will share.
Let's continue your presentation.
I hope it will be fine now. So can you see the screen?
No, oh yes, we see your screen.
So we stopped at the problem of filtering the images corrupted by short noise process. I was saying that we have a method how to approximate the short noise process with a Gaussian process, and that's make life easy. So what we have now? Now we can apply the Kalman filtering for image restoration. So for the Kalman filtering model, we have that the noise-free pixel value is f and alpha is a constant, and this is the autoregressive model for the video, for the image sequence. And the measured signal I is given as the intensity of the true image plus the Gaussian noise. The exact formulas for the Kalman filtering I'm not providing here because it's a very well-known result. I'm just saying that we applied the Kalman filtering to we first took the original image. The parameters of the short noise process are here on the slide. The jump size is normally distributed. The y is the size of the jumps. The intensity of the driving Poisson process is 1.04. And we took our original image, we corrupted it with the short noise, and then we applied our restoration technique, and the result that we obtained was significantly better than the image that was the corrupted image. And we had some here numerical experiments and results. We compared some other methods and calculated the peak signal to noise ratio and comparing. So we had some, with our method, we had some improvement. So this is the end of my presentation. This is what I did not manage to, due to the computer problem, to finish at my time. So I'm sorry for this. Thank you for your attention and for the possibility to finish my talk. And if you have any questions.
Presentation, for your report. We are happy to see you in our workshop. Who wants to ask the questions? Okay, if you know a question, I have some question. Why did the proposed Kalman filtering special Wiener filters and multi-layer perception model? Thank you.
Probably because we chose the perfect parameters. We chose the perfect parameters for our short noise. As I told, that the Gaussian approximation really holds when the jump size is not very big, and the jumps happen quite often. In this case, the really approximation holds, and the filtering result is quite well. So if this condition will not hold, if there will be high jumps and rare jumps, then this technique can fail, probably because we fulfilled all the assumption for approximation. That's why we had a good result. So for another case, if we have such parameters that the Gaussian approximation do not hold, then this is the topic for the future research.
Okay, thank you.
Okay, I have a question. Tell me please, what the proposed Kalman filters approach archive higher? Yes, okay, I'm sorry because I have next stream today. Okay, what's the mathematical difference between short noise and compound portion Poisson noise, and how do three different affect the noise and strategy?
So please look at the slide. So this is the definition of the short noise process. You can see here this exponential decay factor. So the jump decays. The effect, there is due to the camera defect or sensor defect, there is a jump in the intensity of our captured picture, and it also affects the future the next slides, but each time the effect is lower because the short noise decays. And if you look at the compound Poisson process, you see here there is no this decaying effect, so it just jumps. They do not decay. So, but for compound Poisson process, the approximation also holds for the specific condition, and if these conditions are fulfilled, then it works quite well.
Okay, thank you for your answer. And I have one question. What's the next step is your decision?
You mean the future research?
Yes.
I think we will look at such types of short noise which is not approximated very well by Gaussian process, and decide what we can do there. Because if the assumptions are not fulfilled, then we don't have a nice approximation, and then we have to solve another problem.
Okay, great. Thank you very much.
Thank you very much for your questions.
Thank you for a very interesting report, for your presentation, for your answers, for discuss, yes, and we going to the next and final our presentation is Igor Pikevich, Mykola Romanchuk, Olena Naumchak, Matron Fedorchuk, and Leonid Naumchak. Olena Naumchak, are you here? Olena Naumchak, we don't hear you. Maybe you connect with phone, with the microphone. Then share your presentation, yes.
Our seminar is long.
Okay, presentation we see, but we cannot, we don't hear you.
Full screen, please.
One second, please. I will and try to connect with other device.
Sure. The English day today.
One second, please. Also.
Мені здається, що вона взагалі підвісла, ні?
Я зараз хочу побачити. We've got okay. Anyone who wanted to can read this article, you can see this in our proceeding, in the workshop proceeding, yes. After has some problems with the connection, but who want to ask the questions, you can ask this question in our, Olena trying to connect it by phone, 1 second.
Can you hear me now?
Yes, we hear you, but we don't see your presentation.
One moment, please. I just reconnect from my computer.
Recording in progress.
Oh, Olena, please turn off the sound.
Yes, yes. I turn off from my computer the sound, and now you see the presentation. Yes, yes, I see. I check. Let me start, dear participants. I would like to present you a report on the topic shown on the first slide. It's improved model for detecting randomly oriented objects on remote sensing images. The computer vision technologies are widely used to process remote sensing images and to identify objects in the imagery, satellite imagery. It's necessary to solve the task of detecting, recognizing, and assigning accurate bounding boxes or masks for small, randomly oriented objects, separating them from the background and providing for these objects accurate class labels. CNN's models are widely used for object detection. In cases of object detection from a perspective parallel to the Earth, parallel to the image coordinate axis. Classical object detection is the detection of a simple object in an image using a horizontal bounding box. and detecting randomly rotated objects with a large aspect ratio is very actual and arises now. And the problem of effective recognition of randomly rotated objects arises. Using the rectangular bounding box parallel to the coordinate axis for detecting randomly rotated objects with a large aspect ratio increases the bounding box, and as a result leads to overloading of the detector in case of classification. In addition, it doesn't provide accurate information about the object's orientation and scale. To solve this problem, approaches based on the rotation of bounding boxes or other polygonal bounding boxes are used. The known models like ConneNet, CentiNet, or ExtremeNet select and group a set of certain key points of an object, such as corners, peaks, etc., to build a accurate bounding box. But the disadvantage of these approaches is that they don't take into account the cases of complex scenarios on satellite imagery when it's necessary to detect small, densely located, randomly rotated objects, the detection of which remains relevant under such conditions. We used common methods based on 5-parameter regression, which adds the angle parameter in addition to the basis parameter to represent the bounding box in any direction. The YOLO version 11 model architecture is used as the base, which is designed to improve the detection of small objects and increase accuracy while maintaining real-time inference speed. In the proposed model, the image label is pre-processed, in which the processing mainly concerns the label part, and the information about the angle is obtained from the spatial labels of the objects. Data pre-processing allows us to obtain the object's orientation angle. And the network consists of the following parts: the input part, main, and prediction part. Some models are omitted in the figure presented on slide, and only the general structure is shown. The input part is used to extract the features from the image, from which 3 feature maps are extracted, which pass through the main part, where a number of operations are performed on them, such as convolution, upsampling, and combining, etc. In the main part also, to merge feature, we use some modulus, like a multiply maximal pooling operation, to aggregate multi-scale contextual information. Such approach improves the processing of fine-grained object in images. For example, the model cross-stage spatial with spatial attention introduces attention mechanism to that improves the model's focus on important areas of the image, such as smaller or covered objects. It's very important for military purposes. After that, the prediction part produces detection blocks for 3 different scales, low, medium, and high, using the feature maps created by the previous steps. This approach ensures that small objects are detected in greater details, while the larger objects are captured by the higher level features. In the proposed 5-parameter model, regression is used to predict the rotation of the bounding box. Since weapons and military equipment samples on satellite images have a fixed aspect ratio, and the direction parallel to the longest side is defined as the direction of object's movement. Therefore, to facilitate the regression task, the longest side is defined as W and the shorter than H. Thus, the direction parallel to the direction of movement, it's a direction of movement of the object. And the angle between the longest side and the axis is the angle of rotation of our bounding boxes. To accurately determine the angles, it's also necessary to perform a conversion between the 5-parameter method and the 4-point annotation of bounding boxes. The example of coordinate calculation for coordinate shown on a slide. The angle value is added to solve the problem of regression the object's direction of rotation. For example, in a neural network, when processing an input image with 80 image object detection and recognition categories and using the 4-parameter methods to locate the target, the final output matrix is also shown on slide as a quotient 6.5. The result given by the prediction part of the neural network model cannot be directly calculated for the loss function. And to limit it within a given range, we use coordinate and angle regression function. The loss function for training the neural network model for positioning and orienting the bounding box calculate using expressions shown on the slide 7.1. Where the loss function for calculating the size and location of the center using and adding the loss function for the angle. To evaluate the results of the proposed rotating detector model, a comparative experiment were conducted on the dataset DOTA. It consists the images were collected from Google Earth, GovFan second, Jilin-1 satellite remote sensing data provided by China Satellite Data Resource and Application Center, and aerial photographs from Cyclomedia, also including this dataset. DOTA dataset consists of RGB and grayscale images. RGB images are taken from Google Earth and Cyclomedia, and grayscale images are taken from the panchromatic range of GovFan satellite and Jilin satellite. All images are saved in the format PNG. To evaluate the performance of the model, we use the mean accuracy metric, which calculates the average of this score for variable intersection our union values. It allows analyzing a large number of bounding boxes with an incorrect classification to avoid our specialization in a few classes at the expense of weak outputting for our model. And the results are shown on a table shown on the slide, given on the slide. This study, in this study, a rotating bounding box detection model based on CNN architecture YOLO version 11 is proposed to solve the problem of traditional horizontal detectors that have difficulty detecting targets with high density, high aspect ratio, and overlapping bounding boxes. Its available remote sensing dataset was selected to validate the model results and assess its effectiveness. And experimental data and visual analysis shown that our model is an effective choice for detecting and recognizing small-scale randomly oriented objects on remote sensing images. Thank you for your attention. If you have any question, I'm ready to answer.
Thank you for your interesting report. You participated in our workshop every year, and we thank you for that too.
I'm thank you also.
Okay, who want to ask the questions? No? I think we are finished at this moment. Yes, thank you.
Thank you for this.
We thank you all of you, yes, for participating in our workshop. And we invite all authors who presented materials today to submit 30% expanded version of the article for publication in our journal of edge computing. Yes, you know about this. All requests for such articles already sent to authors. And now we ask to turn on the cameras for group photography. Yes, please turn the camera for group photography. Чтобы фотографировать. Олександра Путятіна, Сергій Дементьєв, Віктор Малярський, Дмитро Швайка, Дмитро Шевченко, Орест Печан, Світлана Яремко, Жичен Грі, Бела Голуб, Влад Романюк, Олена Наумчак. Please turn the camera to grow photography.
Може, сядете ближче?
Окей. Ми можемо геть здати.
Можна прикрити до камери. Давайте одну фотографію дивитесь сюди, хай буде з обличчям. Тетяна Миколаївна, давайте одну, що ви до мене дивитесь.
Ти там ще не включали, почекай.
Орест Печан, Жичен Грі,
Може, відійшли.
Олена Наумчак, Найдієс.
Так, фотографую, сюди дивимося. Є. А другу можемо на екран, так?
Yes.
Є. Є. І... Так, Тетяна Михайловна, вас не видно. Чуть-чуть десь. О. Круто, є.
Okay, we thank you for all of you. Many issues related to edge computing were considered today, and a fruitful discussion was held, yes. And I would be happy to inform you that our proceeding yesterday indexed in Scopus, and we invite you to our next workshop. We are held in 2026. Thank you for all of you and to next meeting. Дякуємо ще раз всім і до наступних зустрічей.
Thank you. Bye.
Thank you. Bye.
Thank you.
Дякую,
Bye.
до
Thanks.
побачення.
Have a nice day.
Thank you. Bye.
Have a nice day too.
Так, куди?
Що, вже індексоване.